So let's start with these fundamentals of probabilistic model checking. As I said, then Sebastian will give you some hands-on with Storm. After the coffee break, we will have this fault tree analysis and then finally parameter synthesis with, again, some hands-on using Storm. Good. Let's start with model checking because that's the technique we are going to use. This has been, let's say, very successful in the past. The developers, the originators of model checking received the Turing Award a couple of years ago. And the idea here is that you have a model of the system. This could be a robot, this could be an autonomous car, this could be a piece of hardware and so on. And that you have a property that you would like to check. You put this into what is called a model checker, which is typically a software tool. And that provides you with the output that either the property is satisfied or if not, it also provides you with a counterexample that then you can use to understand why your model does not satisfy the property. So I have a very simple example to make this explicit. It's the wolf, goat, cabbage puzzle that you are all familiar with. We are on one side of the riverbank, right? There is a goat, there is a wolf, there is cabbage, and there is a ferryman, which you see here in the red-white shirt. And the idea is to bring everybody to the other side. But of course, the goat should not eat the cabbage and the wolf should not eat the goat. So what are we going to do? I'm going to show you how you can apply model checking to solve this puzzle, this toy example. So the first ingredient that we need is a model of the system, right? So how are we going to model this? Well, we're basically going to represent all possible scenarios, and you see this here on the left. And almost at the top middle, you see that we start with basically having both the ferryman as well as the cabbage and the goat and the wolf at the riverbank 0. That's the floor trouble that you see in the middle. I don't know, my mouse doesn't work apparently. And then what can happen is, for instance, if from the initial state you can go to the right. And that means that the ferryman takes the cabbage and brings it to the other side of the riverbank, yeah, and so forth and so forth. And finally, what do we want to achieve? We want to achieve that everybody gets to the other side of the riverbank, and that's almost at the bottom of my diagram on the left. It's the one but last state there: C1, F1, G1, and W1, because that's the state where everybody. All objects are on the other side of the riverbank. Now, this is modeling all kinds of scenarios, in particular also the scenario that the wolf can eat the goat or the goat can eat the cabbage. So what do we do next? We will have a property. That's the specification of our system. And in this case, the specification looks like this. It's a temporal logic formula that says our goal, our objective is that we have everybody on the other side of the riverbank, and that you see after the until operator, C1 and F1 and so on. And of course, we have the prerequisite that before this happens, yeah, if there is a wolf and a goat together, then there should also be the ferryman to separate them. And similarly, if there is the cabbage and the goat, there should also be the ferryman to separate them. So that's what is written down on the left. And basically, you're looking for a path that brings the people to the other side of the riverbank while making sure that, let's say, the goat and also the cabbage are not consumed on the way. Now, actually, what we're going to do in the model checking, we're taking the negation of this property. Because if we do this, then hopefully this will be not satisfied and we will get a solution to the puzzle. So if we now apply model checking, we get the following outcome. Right, so there we get a counterexample, and this counterexample tells you exactly, gives you a particular schedule on how to bring everybody else to the other side of the riverbank. You see the final state is C1, F1, G1, and W1, and we start the initial state, and on the way, neither the goat nor the cabbage is consumed. Good. Now, model checking has been applied to several examples. I won't go through all of them, but one of the examples is, for instance, at the Jet Propulsion Laboratory in Pasadena. They work for NASA, and they basically do a lot of model checking for instance, Mars rovers and for the missions that go into space by NASA. Another example where model checking has been quite successful is by a development by Microsoft. They developed a model checker called SLAM, and that was used to check all device drivers, because there the idea is that most errors appear on the interface between the software of the operating system, completely under control of Microsoft, and the software from, let's say, device providers such as HP or Apple or others. And in order to avoid this, they built this model checker, and that turned out to be very successful. And actually nowadays they use this to check basically this interface software. So the topic of today is model checking, but now probabilistic model checking. This does not mean that the procedure is randomized. It simply means that the models that we are going to use have probabilities. Yeah? And this could be used, for instance, for the navigation of a robot, and it could be used to model certain uncertainties. So here you see some examples where we use them to model random phenomena. So random phenomena are, for instance, used in the robot motion planning. There you see this on the left. And there you have a kind of a labyrinth, and you would like to find the exit at number 12. And you would like to basically find a policy for the strategy, a controller for the robot, that if it starts, for instance, at position 5, it can safely find the exit. And the problem here in this example is, for instance, that the robot can only see the colors, so it cannot distinguish, for instance, position 5 to position 10. And then this question actually turns out to be quite hard, and the solution is already indicated in the picture, but that's where random phenomena play a role. Reliability analysis is something we're going to cover after the break. In biology, you have molecules reacting to each other. That turns out to be something like a continuous time Markov chain. So that's something which is random. But also we have experience with the European Space Agency. Mostly security protocols are randomized. And in self-driving cars, like in robots, you have to cope with uncertain phenomena in the environment. And typically randomization is a way to solve this, to get at least to cope with this. So what is probabilistic model checking? It's an automated technique that now takes as input a finite state probabilistic model and a property, a specification. And then you would like to systematically check that, for instance, the probability of such a property holds. So basically the way to see this is that you have, for instance, a model M, and we are going to see two different models. Actually, we're going to see Markov chains and Markov decision processes. Then you have a kind of a logical formula, something like a formula we just have seen in the example. And then we ask ourselves, is the probability that this formula holds in the model, for instance, larger than a half or equal to 1, yeah, or strictly positive? These kind of questions we would like to, you can address with probabilistic model checking. Okay, this probabilistic model checking is relatively, goes back to early work in, for instance, two seminal papers that I like to mention. One by Kostas Kourkoubetis and Michailis Ganakakis on model checking on Markov decision processes. And later by these people from Sweden, Hans Hansson and Bengt Johnson, who worked on probabilistic CTL. So they both use different languages to describe their properties. On the one hand side, linear temporal logic. On the other hand side, a branching temporal logic. This requires different procedures. I'm not have the time to go through explaining all these kind of different procedures, but it's good for you to know that these procedures are there. And now they also have very efficient tools to deal with these kind of questions. Good. So roughly what is probabilistic model checking? On the left-hand side, we have on the left top, we have something that describes a probabilistic model. This could be a PDDL program. It could be a Petrinet. It could be a kind of other description that describes your system. So here, this is a small program. And actually within the square brackets P, this means that you flip a coin, which is biased, and assigns 0 to X with probability P and 1 to X with probability 1 minus P. And similarly for Y. Now, what you do, this model checker compiles or transforms this into a model. And typically model checking confines itself to finite state models. So think about graphs where you have probabilities attached to those edges. On the other side, we have a system requirement, like we had for the wolf, goat, cabbage problem. And now these requirements look, for instance, like the formula there that says with probability less than 1/10, eventually, future, we will reach a fail state. And now we have this finite model, we have this specification, and they are both input to the model checker, and the model checker will either say, well, this property is satisfied. But the nice effect of a probabilistic model checker, it will also give you quantitative results. It will not answer, is indeed the probability less than 1/10? It will also compute the probability up to some accuracy epsilon. Let's say up to 8 decimals or 10 decimals, it can compute this correctly. So you can also get plots like indicated on the right. Or if the property is violated, then in many cases, you're also possible to find counterexamples, similar as what we have seen in the golf goat cabbage example, but the counterexamples are more complicated. And the tool we're going to use and we're going to illustrate and demonstrate later is called Storm, and you find this at stormchecker.org. So I want to give you one small example, and this is called the lost passenger ticket problem. So we have a fully booked airplane. Every seat is fully booked. Every passenger has its boarding pass except the first passenger. So the first passenger apparently lost his or her boarding pass. And what it does is this first passenger is entering the plane. He or she lost his boarding pass. So what does the person do? It randomly picks a seat. Okay. And now all other passengers enter the plane. They all have a boarding pass. So what do? Well, if the seat on their boarding pass is free, of course, they're going to be seated there. Otherwise, they're going to randomly pick a seat. Yeah, because it could be that their seat is occupied. Question, how likely does the last passenger get the seat on her boarding pass? Now, you can model this by a program. I will not go through the details of this program, but E is, for instance, the capacity of the plane. So here is E is, for instance, 1000. And then the first passenger enters, so it rolls a die, and it picks a certain seat with probability 1/E. And that's then the seat that is taken, and the number of passengers is decremented by 1. And in the while loop, all the other passengers enter the plane, and they all have a ticket. Now, in probabilistic model checking, you can solve this, and you see this on the table on the right, where we change the capacity of the plane a bit from 100 to 10 million. And it tells you in how much seconds you can solve this question by means of probabilistic model checking. And if you think this is a bit ridiculous, I mean, there are planes like this where you can really, host many passengers. So what kind of probabilistic models are there? We distinguish between discrete and continuous in one dimension. So discrete means you have discrete steps in which those systems evolve. Continuous means you have some kind of continuous time evolvement in the system. I will not, let's say, illustrate that part. We will use it in the applications, but I will not go into the foundations of it. And then you have deterministic models, and then we're going to talk about discrete time Markov chains. And you have models with non-determinism that I will show by means of some example. Now, there are many other models out there. I mean, there are, for instance, in AI, what is frequently used are things like Bayesian networks, but Bayesian networks are basically equivalent to Markov chains. You also have partially observable MDPs. Well, they are a kind of infinite state MDPs. You have stochastic games. You have probabilistic pushdown automata, which are a kind of infinite state Markov chains, and so forth. And then there are different properties. I already mentioned in the early days, you had people working on LTL. I have this in this basically in the third column. And LTL you can also represent by some kind of automata model, like a deterministic finite state automaton or a deterministic automaton accepting infinite words. And then you have logics, for instance, branching time logic like probabilistic CTL. And if you have continuous time, you basically have timed versions of all this. And the core problem in model checking is to compute the probability to reach certain states. Now, and the way I'm going to do that is I just give you a very small example to give you a kind of a grasp what's happening. So suppose we have this 4-state Markov chain. We start in S1, and we are interested in reaching the green state, S3. Okay, so we are basically want to ask, for instance, is this green state reachable with at least 0.75? So how are we going to solve this? We're going to associate to every state a variable, and this variable you can think about as a probability. So this is a value between 0 and 1. And the idea is that this is the probability to reach the green state. Then I hope it's obvious to you that for the green state itself, this probability is 1. For state 0, the probability is 0, because completely from the leftmost state, you cannot not reach the green state, right? So that will be 0. So the only interesting cases are those two states in the middle. So what do we get for state S1? We're going to look at the outgoing edges. So I'm going to say for P1, the probability that S1 can reach the green state, well, either with 7/8, it moves to S2. So we multiply this with the probability to go from that state to the green state, that's P2. Or it moves to the left, which is a bad decision, of course, but that's what happens with probability 1/8. And then you happen to be in state S0, and for that we already know that this is 0. And similarly, you had an equation for P2. And this is now a linear equation system. And how can we solve the specification? Well, we solve this by checking whether the probability of P1, the initial state, is at least what is written down in the specification, 3/4. So what this example shows is that the key on doing model checking is solving these kind of linear equation systems. And there are efficient techniques to do that. You can either, non-efficient techniques are things like Gaussian elimination, but there are iterative methods like value iteration for which you can solve this quite quickly. So what are the kind of properties you can do with model checking? Well, you can, for instance, say, well, is the probability to reach a bad state, a state which is not safe, is that below, hopefully a very low value, 0.001? Or is the probability to reach the goal state, hopefully a success state, within a certain deadline, let's say 2 days, above 0.9? Or is, in terms of models that have non-determinism, is the maximal probability to reach the goal without collisions above a certain threshold? There are also extensions of these Markov chains where you can model things like costs of energy consumption. And then you can also address questions like this. What's the expected number of steps until reaching the goal? So that's basically taking what's the expected number of transitions until you reach the goal state. Or in the biology example, what's the expected concentration of certain molecules after a certain amount of time? Or in terms of energy consumption, what's the minimal energy usage to reach a goal? And you would like to reach that goal with a very high probabilities, or very likely, let's say, with at least 0.999. These are the kind of questions that you can address with model checking. You can also address more complicated questions. So this is perhaps a bit technical, but let's say we have this Markov chain here on the left. Every state is labeled with some, let's say, elementary properties. In my case, these are the letters A and B. And now I have a property that I represent by this automaton. And the property says the Markov chain should have never B and infinitely often A. That's what you can represent by this automaton. And this automaton represents this by reaching the state Q1, because you can only reach Q1 by an incoming edge that basically has not B, and it is also labeled with A. And now the additional requirement is you have to visit this state infinitely often. So it's not like a finite state automaton. It's an automaton that actually accepts infinite words. Now, again, you can model check this. So now you're interested in what's the probability that your system, represented as this toy Markov chain on the left, satisfies this property on the right. Yeah? You're never unsafe, and you're infinitely often doing something good. Now, what you can do, and I'm going to skip some of the technical details, is that you can now build a kind of a product of the yellow automaton, the yellow Markov chain, and the automaton on the right. And this gives rise to this picture on the bottom. And now you can reduce this to, again, a reachability question, because now what is an accepting, let's say, part of this Markov chain? Now, it's a finite Markov chain. So what does that mean? It means that with probability 1, it will end up in one of the boxes, one of the gray boxes, or let's say this blue box on the left bottom. And now you have to basically distinguish what are the good boxes. So the good boxes is, in my case, the blue box. Why is this good? Because there I visit Q1 infinitely often. If you look at the two gray boxes, you don't see any appearance of Q1. So you will not be visiting Q1 infinitely often. Well, and that was the specification. You need to visit Q1 infinitely often. So those boxes are bad. And now what you need to compute is the probability to reach, in my example, the only one, let's say, acceptable box, which is the box in the left bottom corner. So again, it's reachability. Again, it's solving a system of linear equations after doing this product and some graph analysis. So herewith, you can also address much more complicated questions. How does this scale? So here you see a plot that we computed with Storm with several different measures. So the red boxes are reachability queries, the queries that you just have to solve, let's say, a system of linear equations. You can also have bounded reachability, so that means you need to reach a certain set of states within a certain number of steps. You can also have costs. Costs in this context are rewards. So the light blue circles, they say something like, what is the accumulated, so the total cost that you have accumulated over the whole trajectory, for instance, until you reach a successful state. So these are the light blue circles. And then you can ask other questions like, for instance, steady state, which are the red crosses. And steady state basically means your system needs to be in some kind of equilibrium. And being in an equilibrium, you're interested in what's, for instance, being in an equilibrium to be in a good state. Now, what the plot shows you is that you can actually deal quite large systems. On the x-axis, you see the number of states in log scale. On the y-axis, you see the runtime in seconds, also in log scale. So just to put this here, I mean, this is model checking 1 million states, right? And in a time frame of 100 seconds. And everything within this red box, you can solve within this amount of time. And if you even go larger, if you give your model checker 1000 seconds, then you can even handle many models that have about 10 million states. So this technique, since, let's say, the end of the 80s, has been evolved a lot by efficient algorithms, by symbolic techniques, by all kind of techniques to minimize the model before you do the analysis and so forth. Good, and here you see another plot that shows something for a tool competition, the most recent one. On the x-axis, you see the number of problem instances that can be solved. On the right, on the y-axis, you see again the runtime in seconds in log scale. So this is what is so-called a quantile plot. So it means the lower the curve, the better, because you can solve more problems in lower time. And you see that the tool Storm, which is indicated by the two blue plots. Why do we have two? Because you have two modi in which I can run Storm. And what you see here is that we outperform other existing tools. For instance, the orange plot is by a tool in Oxford. The red one is something in Twente in the Netherlands. And you see that Storm is doing extremely well in these competitions. Okay, this was all about Markov chains. I now would like to introduce Markov decision processes. And I do this by means, again, of a kind of a toy example. It's a 2-coin game. So we have 2 coins, a €2 and a €1 coin. And they're both biased. So what does that mean? I flip the €2 coin, and I get heads with probability P and tails with probability 1 minus P. And similarly for the, let's say, the €1 coin, I get heads with probability Q and tails with probability 1 minus Q. And now we play the game. Yeah, if you get heads for €2, you gain €2. If you get heads for €1, you gain €1. But if you have tails, right, then the game is over. Good. It's up to the user to pick one of the 2 coins. So you can either select a €2 coin, then again a €2 coin, then maybe you flip a €1 coin and so on. But what do you want to do? So you have those 2 coins. We repeatedly choose which coin to flip. And either we receive some euros, 1 or 2, or we lose the game. Yeah? We start with some initial budget, typically 0 or 1. And you win the game once we have won at least n euro. So n could be 3, 4, 5, and so on. And now the question is a bit, what should we do? What is our strategy to maximize the chance to win? Now, you can solve these kind of queries with probabilistic model checking. There we need to know what is P and Q. Actually, Sebastian will tell you later, we can even deal with models where P and Q are unknown. So exactly with this example. But of course, N needs to be finite, right? Good. What's the point in model checking? You can solve not only, let's say, you can compute what is the maximal probability that you will win, but you can also distill the strategy. So as a byproduct of the model checker, you synthesize, so to speak, this strategy. So maybe we look at an example. So that was the game, right? And now we have this example. So this is an example where n equals 2. So you start in initial state, x is 1. Now you have to flip, you have to decide which coin to take. And notice this choice is non-deterministic. It's not the case that in 50% of the cases you take the €2 coin, and in 50% of the cases you take the €1 coin. You really non-deterministically, you check one, you flip one of them. And then it's clear, if you flip, for instance, the €2 coin with 1 minus P, you get tails, so you lose, you go to the left state, and with probability P, you will earn €2, and that means your budget goes from 1 to 3. And similarly for the €1 coin. Okay, and it's not difficult to see that the best strategy is if P is larger than Q, right? You better take the €2 coin. If P is less than Q, then you better select the €1 coin. So that's your winning strategy, so to speak. As I said, with model checking, you synthesize these kind of strategies. What happens if you have n equals 3? Well, then the situation is a bit more complicated. You start with x equals 1 as before. But now, for instance, you flip, let's say, the €1 coin in x equals 1. Now, if you're lucky, then you get heads. Then you are in the state x equals 2 because you earned €1. But now you have to make a choice again. So here you see that you have to solve both non-deterministic choices. And now the situation is already a bit more complicated. And if you look carefully, the best strategy is that if P is at least Q square, so Q, then you better flip the €2 coin. Yeah, because if P is larger than 2 square, in the initial state, you better take the €2 coin with probability P, you will win. But if you would take the €1 coin, yeah, you have to flip it twice, and that's why we get the Q square there, right? If P is less than Q square, you basically flip, the best strategy is to flip the €2 coins. And actually, if P equals Q square, yeah, then it even doesn't matter. Your strategy, I mean, what you take, you will earn the same thing. Good. So what you can do in these kind of models, you can compute what is called the minimal reachability probability. What's the worst possible, the lowest probability for all possible strategies to reach a certain state, like earning n euros, or what is the maximal reachability probability? Good. And there are models, for instance, AI, where you also have discounting. Discounting intuitively means every time you take a transition, you basically you think that the let's say the old transitions are less relevant. So you multiply the probabilities with a kind of factor, which is called a discounting factor, which is typically smaller than 1, strictly smaller than 1. Good. Now, the interesting thing is that for reachability, simple strategies suffice. And what is a simple strategy? We call this a positional policy or a positional strategy. That's a policy that only looks at what is the current state, and only based on the current state it can decide, well, we either pick the €2 or the €1 coin, that will be optimal. Yeah. And the cool thing is that you can, there are very efficient techniques to obtain these kind of policies, value or policy iteration or linear programming. Now let me stress that reachability, as for Markov chains, I showed you that reachability probabilities are the core essential ingredient in model checking. This is the same for Markov decision processes. So you can also use this to verify much more complicated properties on MDPs. They almost all of them reduce to solving these kind of reachability queries. Good. So let me show you again a simple example to show you what's going on. I have an example on the left. And the only non-determinism is in S3 and in S0. Now, what is our objective? The objective is we would like to minimize the probability to end up in the state that is labeled with A. Now, if you look at S3, there are two possibilities. Either with probability 1, you go to S2, or with probability 1, you take the self loop. Now, what is the worst possible strategy that you can take? Well, the worst possible strategy to reach this A state is, of course, to take the self cycle, because then you will never reach S2. And that means that the probability from S3 to go to S2 is 0. Now, in S2 itself, it's clear the probability is 1. So the only thing that we need to solve, what are we going to do in S0? Now, in order to do that, you can set up a linear programming problem. It's written down on the slide on the second dot. And that linear programming problem says you would like to maximize the sum of the probability of S0 and S1. So again, as for the reachability, we're going to attach to every state a variable. In my case, these are the X variables. And the idea is that those X variables represent the minimal reachability probability, or the reachability probability to reach the A-labeled state. Now in S0, we have two choices. Namely, we can either move up to S1 with probability 1. That gives rise to the first inequality. But the other inequality comes from the fact that in S0, you can also take the other option. And the other option is either you, with probability a quarter, you take the self cycle, or with probability a quarter, you go to S3, which of course is, let's say, a decision that leads to the target state with probability 0. Or with probability half, you immediately get to the target. And that gives rise to the second inequality. And the third inequality comes from the state x1. And that's just a Markov chain state. So that is basically the same as your linear equation we saw before, but now it is an inequation. And if you look at this graphically, you get the picture which is at the bottom of the slide. Yeah, you get those inequalities. They are all, let's say, the lines in my program, the lines in the picture. And now we are interested in maximizing the sum of x0 plus x1. So we're looking for the solution, which is the red dot. And in this example, it turns out to be 2/3 and 14th over 15. And as a byproduct, we also can get a strategy, and what turns out to be the optimal strategy here. The optimal strategy for S0 is actually not to move to S1, but to take the other edge. Good. You can also compute this iteratively. You see the iterative computation here on the right of the slide. And graphically, this is the red line that you see in the computation. Of course, in the end, we approximate, again, this red point, which was this maximum of x0 plus x1. And you do this now iteratively. Good. Here are some statistics for Storm to do model checking. This is explicit state, so we do not use any symbolic techniques in this curve. It's really about solving this linear inequation problems iteratively. And here again, you see on the x-axis the number of states, log scale, and the runtime in seconds, also log scale. And also here, you see that 1 million or 10 million states can be dealt with in 100 up to 1,000 seconds. Good. Now, for MDPs, for Markov decision processes, we have so far considered one objective. Either you would like to maximize the probability to earn a lot of money in terms of the game, or you would like to minimize the probability to reach a bad state. But in MDPs, you can also look at multiple objectives. So you could, for instance, have a trip to the airport. You would like to catch your flight. There's several options to travel to the airport. You can go by bike, you can go by cab, by car, you can go by tram. There are several means, but these are all, there are certain uncertainties. You can end up in a traffic jam. If you're in Amsterdam, you can end up in a bike jam, actually, and so forth. Yeah. And then there are costs, and maybe that's the travel time. So you would like to maybe minimize expected travel time. For instance, the expected time that you get to the airport is 2 hours. And you also would like to maximize, for instance, and that's even better, to maximize the probability to arrive before your flight departs. But then there are other types of cost. So maybe you would like to not only to maximize the probability to arrive before the flight departs, but you also would like to basically, for instance, maximize the probability to use no more than, for instance, 50 euros, because that's your maximal budget that is available to travel from your place to the airport. Now, you can model this as an MDP. You see this in the picture, right? Again, you can here take the car or you can walk. And with certain probabilities, some things, some trajectories will take you longer or will maybe not lead you to the airport and so on. But what is important on this slide is we have several objectives. The objective to maximize the probability to arrive before the flight departs and to maximize the probability to do this within your budget. Now, so what we're looking for is what is a strategy that can actually achieve both objectives at the same time. Good. And this gives rise to, and you can imagine that these objectives are basically can sometimes conflicting. So actually this is a kind of a trade-off analysis. So here is a very small example. You would like to arrive at the airport within 3 hours, but your budget is 50 bucks. So you don't want to invest, you would like to invest less than 50 euros. So this is a kind of a trade-off, and you see this trade-off in this plot. So you see the probability to reach the airport within 50 euros on the x-axis, and you see the probability to reach your flight on time within 3 hours on the y-axis. Now, certain strategies are maybe not realizable. These are the one in the white area of this, let's say, this area. Because, for instance, it could be the case that you need more money, but then you will be there very fast. Yeah, so that's not fulfilling your strategy because you would like to reach your target within 50 euros and you're not willing to spend 100 euros. That will definitely bring you to the airport very fast, but that's not an achievement. That's not meeting your objectives. So actually this trade-off analysis is all about computing this green area. And this green area is actually determined by what is called the Pareto curve. And the Pareto curve is a convex area. And in this case, it's downwards closed. That means if you have points on the Pareto curve, everything which is, let's say, below it is also in the Pareto curve. That happens if you, for instance, have lower bounds on your probabilities. So this is all about computing these Pareto curves and dealing with those trade-offs. And this is also something Storm can do. Good. So just to show you a bit what you can, how these policies look like. Well, now we need policies with randomization and memory. Remember my game with the €2 and €1? I mean, there, well, we don't need randomization. Either we took the €2 coin or we took the €1 coin in all of the states, but it was never the case that we were basically, flipping another coin by saying, well, in 50% of the cases you take the €2 coin, and in 50% of the cases you take the €1 coin. But now we need this. And a simple example to show you this is this example. So this example, you have a non-deterministic choice in the initial state S. And that says if you take alpha, then with probability 1, you go to the left. But if you take beta, then with probability 1, you go to the right. And now I would like to have that, I would like to be able to reach the red state with probability half. And I would like to reach the blue state with probability half. So I'm asking myself, is the point a half? Is this in my green area? And my green area is called the set of achievable points for this specific two multiple, let's say, reachability queries. And it's hopefully clear for you. You can only achieve this if in state S you're going to flip a coin, right? Notice this coin is not part of your model. It's a coin that is part of your policy, of your strategy to solve this puzzle, right? And then you check, you basically go to the left with probability half, and you go to the right with probability half. And then it's clear, you will reach the red state and the blue state the way you want it to be. Now, if you make this example slightly more complicated, the only thing I added was a back edge from T to S. And now you're interested in the following question. Can I reach the red state with probability 1? And can I reach the blue state with probability 1? So is the point 1, 1 in my green area? Is this achievable? And indeed it is. But now you need also memory, right? Because it's clear that if you are in the initial state, you want to reach blue and red. So in the initial state, in the beginning, you should not, let's say, select beta and go to the blue state, because then you have no chance to reach the red state anymore. So you better go to the left initially. So what does that mean? If you did not visit the red state before, you go left. But now you go back from right to the initial state, and now you have to again make a choice. Well, and now you should favorize to go to blue, because at least after a couple of times visiting a red state, you should decide to go to blue, for instance, if you have visited the red state once. So we have a policy which now needs some memory, because it needs to keep track of the fact, did I visit the red state not, or did I visit the red state before, or did I not visit the red state before? Good. So what Storm does, it can compute these kind of achievable points, and it does this iteratively. And you see this basically in this picture going from the top left to the bottom right. So initially what we do is we basically select a vector, and this vector is indicated here with W. And then we can compute this point PW. This point will be part of the Pareto curve. And what do we know then? Well, we know that all points that are to the right, so above PW, we say, they are dominating PW, they are not achievable. So that gives us immediately let's say, the red indicated triangle. And we know that all points that are basically in the convex hull of the downwards closed of PW are achievable, and that gives rise to this, let's say, green rectangle. And now we continue. We select a next vector. This is the picture in the middle. This is the vector W that points to the north. This gives us another point, PW. That's also part of the Pareto curve. And as before, all points above it are now not achievable. So you see what happens to the red area. And everything, let's say, that is in the downwards closed convex hull of it is actually green. And this continued. So in the last picture, I showed you one other vector that goes basically to the east. And that vector basically gives rise to a more, let's say, extending the green area and extending the red area. And you do this iteratively until at some point, yeah, I would say the white space between the green and the red area is almost vanished. So in this way, you can compute these achievable points. And this has been implemented in Storm. So here you see there are other tools as well, but we concentrate on the last column. So this is implemented for Markov decision processes for different objectives. So reachability probabilities. That was the example that I just showed you before. You would like to reach the red states and you would like to reach the blue states with certain probabilities, and you're looking for a strategy that computes this trade-off. But you can also mix this with, for instance, total reward properties. What is the total amount of costs that you earn or that you have to spend until you reach your goal state? You can do this also when the system is in a stationary situation, that's what is called long-run average rewards. You can ask, what's the probability that you will reach my target state within a certain budget or within a certain amount of fuel consumption that is reward bounded. And actually, you can even mix LTL objectives in a lexicographic way, and we can compute those trade-offs. So the kind of queries that Storm can handle is what is called achievability. What does that mean? It means you give me a point, a half and a half, or 1-1 in my example before, and you ask, is this achievable? That means, is there a randomized policy that can achieve exactly this point or not? We can also ask numerical queries that basically means that in one dimension you can optimize, and you can ask in what's the maximal value of one particular point, one particular, let's say, coordinate in this point when you solve this multi-objective query, and you can compute approximately these Pareto curves. And this is in Storm, and I show you two plots. These are scatter plots. So let me explain them what they represent. So let's look at the left plot. In the left plot, you see on the x-axis the number of states, again, log scale. And you see on the right axis the amount of time that we need to do sound value iteration. That's what SVI refers to, and that's also in log scale. Good, and then you see several objectives, and you see that we mix the 2 or 3, 4 or 5 objectives. Now, the more objectives, the harder this problem will get, because many approaches are exponential in the number of, let's say, objectives. So it's clear that if you have 4 and 5, then we see already that we are in the upper part of the picture. But for 2 and 3 objectives, we can deal with, 100,000 states or up to 1 million within a reasonable amount of time. On the right plot, that shows you the complexity in terms of, this Pareto curve. How many points. I mentioned this is a convex area. That's convex with finitely many corner points. Now, how many corner points does it have? That's on the x-axis. And again, on the right axis, you see again the amount of time that this iterative approach to compute these points with using sound value iteration. And also there you see with different numbers of objectives. And the termination criteria that we used here, and the termination criteria is basically indicating how much white space is left between the red and the green area. That's at most 10 to the power minus 4. So, I mean, I would say rather tight. Good. Now, I'm getting towards the end. I showed you two, I would say, basic models, Markov chains and Markov decision processes. You see a bit them on the right of the middle of my picture. Now, there are many other models. There are models that have continuous time, and then we're on the left of this picture, continuous time Markov chains. These are also in Storm. We have models that combine non-determinism and continuous time. These are called Markov automata. These are also in Storm. But there are also models that are not in Storm, or only, let's say, only partially. So stochastic games, we use them partially, but they're not. We don't have a full-fledged support for that. And one of the active research areas, for instance, and it's also where we and also Sebastian are working on, is this model used in AI a lot. These are partially observable MDPs, and you see them on the right in the basically the middle of the right of the picture, POMDPs. These are used a lot in AI. Now, let me mention one other model in AI which is used a lot is Bayesian networks or sum product networks, or you have different variations thereof. What we looked at intensively is can we also use model checking for them? And the answer is yes, because basically you can model them as either Markov chains if you have static Bayesian networks, and if you have dynamic Bayesian networks, you can use MDP. And then for them, you can use Markov chain model checking and MDP model checking the way I presented also to solve Bayesian networks. And this turns out to be rather competitive with traditional techniques to solve Bayesian networks. Good. So this brings me to the end of my part, but maybe there are questions and I'm happy to answer them before handing over to Sebastian.
I think there's one question, Christoph.
Yeah, so thank you for the introduction. I would be interested in, you said you're building a linear system of equations, and this you would solve with an iterative solver. And for this, like the properties of the matrix, especially the spectrum of the matrix, is very important. So what is known about the properties of the matrix? So it's a dense matrix, right?
Well, it depends a bit on the structure of your Markov chain. It's typically a sparse matrix.
Okay.
And of course, there are traditional techniques to solve linear equation systems, right? But it works the best if you solve these linear equation systems iteratively. And you do this by what is called topologically value iteration. So that means that you also take the topology of your Markov chain into account. Roughly speaking, if you look at the graph structures, you look at the strongly connected components and you basically compute, you do value iteration and iterative approach in isolation of a strongly connected component. And then you use that in computing also that for other strongly connected components. So this is one trick. Another trick is that we first make the model smaller before we analyze the linear equation system. So we do minimization techniques using bisimulation minimization that typically gives rise. The first initial step that I should have maybe mentioned is that we do a graph analysis. So all the states that can never reach our goal state are, of course, immediately removed. And all the goal states get probability 1. So the only things that you need to solve, or actually if there is a probability to reach the goal state with probability 1, you remove all those states because you don't have to solve the linear equation system for them. So you really try to first make the system or let's say your linear equation system as small as possible before you really solve it. And then you use those topological value iteration techniques.
So the dominating cost is the solution of the system. It's not the pre-processing step. Like
I
the
wouldn't
graph
say
analysis
it's the dominating cost. The dominating cost is the number of iterations you need. And that is typically determined by the ratio between the largest and the smallest probability in your Markov chain, because that determines the convergence. Yeah.
Yeah, I see. So is there work on preconditioning these systems? So this is what we would typically do, to reduce the iteration numbers. You could like get preconditioners which somehow work on the spectrum of the matrix of your system, to precondition it, that your iterations, you reduce the iterations a lot. Like this is the goal.
If I may interrupt here, so for us at some point this becomes a black box, but we're using for example the eigen or so GMM++, or so there's a variation of backbones that we have, and most of these libraries do have preconditioners that are used in order to run this. So the default setting in Storm is to use some of these preconditioners and then to use a Gauss-Seidel style value iteration, like Joost-Pieter said. So the answer is yes, but we at that point the user needs to know some things about the system in order to understand which preconditioner to use. So we have a default there. If you know a lot about your system and you know some linear algebra, you can be much faster than.
I guess. Thanks for that.
You're absolutely right there. I just wanted to clarify that. Right, we have a number of black boxes that if you know how to use eigen, or you know what the options are in eigen, then you can use the model checker to use eigen the way you want. I assume you can all see my version of the notebook. It is slightly different in form because these are slides rather than the notebook itself. But the content, I hope you will find, is actually the same.
Maybe we can quickly say what's the name of the notebook. This is a Storm hands-on on the JHub. And then you have basically the same cells, not just not in presentation format.
Yeah, and feel free to interrupt me at any time. We're well within the schedule, and I can go faster or less fast. There's no actual need to go through the whole notebook, so because you will get it afterwards anyways. So if you feel like you want to have a discussion with me, please do. I'm happy to have that. Okay. So let me start. We're gonna continue basically where Joost-Pieter left off. He a couple of times mentioned that you can do things with Storm, and in these next 30 minutes, I want to show you that you actually can. So Storm is a modern probabilistic model checker. It's state of the art. It's very modular. I already alluded to that a little bit. You can use different solvers for each task. You can exchange the libraries. It's a C++ library, but we have a Python interface, and we'll also go into that Python interface later in this hands-on session. It's open source. We've been developing it for over 10 years now, and the C++ library alone is currently over 200,000 lines of code. And that's going up and down because we're also constantly removing parts that are no longer state-of-the-art. You can get Storm on your machine. We have native support for Linux and macOS. There's different formulas for different build systems in order to get the binaries directly on your system. You can build it from source, or you can get virtual machines and Docker containers that we're constantly deploying using continuous integration. So having said that, you can try whether you can actually run Storm in your browser by executing the command with Shift-Enter. It will take a little bit because these connections are a bit slow, but then it will tell you which version of Storm you are running. If you want to know more about that, you can, for example, add -- version. And then I will have to scroll down here a little bit. You will see some additional output on how this was actually compiled. And for example, you can now change this and get the help. I will not, of course, go into that right now, but this is the idea, and you can play with this during the presentation, but also afterwards. Okay, so let's go into a concrete example. This is the so-called Knuff-Jou die. I will zoom in a little bit. This models a dice roll with a fair coin. So the idea is, I'll give you a coin, and you want to model a 6-sided die with that. And if you think about it, you can think a little bit like a rejection sampling kind of algorithm. So you will flip coins 3 times. If you would do that, you would have 8 different possible outcomes. And so that means that for some of these outcomes, you actually would have to restart. Now, Knuff and Jou said like there's a better way to do this, and this is protocol that they provided is shown on the left as a Markov chain. In every step, you flip a coin in every state, and then with probability half you get heads, and with probability half you get tails, and you update the state in which you are until after 3 or more steps you reach one of these bottom states, and these are the final die outcomes. My claim, and that's not originally mine, but that is that this will have a probability 1/6 to reach any of these states. So how can we check that using Storm? Well, the easiest way to do so is we first need to get the model into Storm. This is a very elaborate format that is hard to, well, it's not very compact, but it's very easy to understand. These are these direct encodings. So there's a little bit of information on the top that we ask you to provide, and it's not important right now. There's some documentation on this. But here we are saying that this is a discrete time Markov chain. There are no parameters, there are no reward models in this system. We have 13 states, and the number of choices or the number of actions is actually the same as the number of states. It's also equal to 13. And then we provide the model. So the model in state 0, this is also the initial state. And then there are 2 possible transitions. With probability 1/2, we will go to state 1, and with probability 1/2, we will go to state 2. And then in state 1, with probability 1/2, we go to state 3 or 4. Yes, Michael.
Yeah, just a quick question about tooling. So, because I've never seen things like this or Prism. I just wondered, just from practical perspective, how do you write this? Are there tools to help you define this, or do you create it programmatically and then print it? Or because if I were to write it, I would make a mistake in some of the space bars, and then I think it would crash.
Great question. So this format we particularly provide for people that want to play around with it. It's not very convenient if you want to do this for thousands or 100,000s of states, right? But if you want to play around with it, this is easy. And what we see is that most people write a small programmatic tool in their favorite language to output these textual files. Later during this hands-on session, I will actually show you other formalisms, languages that make it easier to generate huge Markov chains, right? With this would be a thing where you need another tool to actually generate this for you, or I mean, for let's say 13 states, you would just write this by hand. This is just to get you started.
Is there some kind of agreed upon standard way of generating these things?
Yes. So there are 2 different standard languages, I would say. I will get to one of those in a second.
All right, thank you.
Okay, so I hope you roughly get the idea. We can, with a textual format or using the Python interface, we can basically one by one give the states and the transitions, right? That's the idea of this kind of a format. It's not concise, but it's simple to get started with. And then you can run Storm. So what do you need to provide? You tell Storm, hey, we have in this explicit DRN format a file called in this folder examples. It's called knufjouwdai.drn. And additionally, in order to show you what's actually going to happen there, we're going to tell it, don't try to optimize how you build this model, but build the full model as it's specified in the DRN file. If you do this, you get some information on the top. I will later on, we will always hide that from you, but this is what the Storm would actually output. And then you get some of the basic information saying this is a DTMC. It's a sparsely represented matrix that we're using to represent this DTMC. In particular, we have 13 states and we have 20 transitions. This also highlights that this really is a sparse matrix because there are 169 entries in the matrix and only 20 of them are non-zero. There are no reward models and some of these states are labeled. So we labeled the initial state, but I also provided labels to say this is the outcome where you are in one on the bottom states, and then for the different outcomes, each state is labeled. If we have this, then we can also say, okay, now nice, we have a model. We also want to get a property. So here the property, similar to the syntax that Joost-Pieter already showed you, says, what is the probability to reach, to eventually reach the outcome number 3 with the standard syntax that these model checkers agreed upon. And then you see here that we are model checking this, and the results will say, well, this is roughly 1/6. We also provide you the times, so you can see in these models, this is all rather instant. So that's basically computing reachability probabilities using Storm. It's the kind of minimal interface to start using Storm. Now you can also ask other questions. For example, you can ask, what is the expected number of coin flips that we need? And for that, we use this T operator, which stands for time. We're in a discrete setting, so time and steps is roughly the same thing. And then we ask not what's the time until we get to a particular state. That doesn't make that much sense in this setting, but we rather ask what's the time until we get any of these outputs. And then what you can see is that you need 3.6 steps on average in expectation in order to get to an outcome. Okay, so there was already this question before about, well, is this really the way you want to interface or provide your model to the model checker? And the short answer is no, you don't really want to use this, especially not for Markov chains that are typically huge. We provide a couple of different languages. In particular, we provide this Prism language. This is the de facto standard for human-generated input, because it's there's some GUIs that you can use in order to generate the Prism language. It has a rich tradition. And then there's the Jani modeling language. It is similar to Prism. It's a bit richer. It's harder to write as a human, but it's a JSON-based format. So it's very easy to generate programmatically. And then there are these explicit formats. I just showed you one. There are a couple of others based on, for example, MATLAB matrices, NumPy matrices, etc. We support them natively. There are versions of Petri nets that can be nice, and we will see later that fault trees are also natively supported by Storm. So let me give you a short introduction into this Prism format. So here first is the knufjouwdai, but then as a Prism format. This is the naive encoding. This is not what Prism formats are intended to be, but I want to show you some things here. And I deliberately, you can look at the whole file if you want to, but I'm deliberately focusing on the essential aspects. So the idea here is that there's now a variable. That variable is called S, and it will encode the state. We can have multiple variables later, but right now we have one variable. And then we also provide the list of transitions. And now we're saying, well, if S is 0, then in the next step with probability a half, S will be 1, and otherwise with probability a half, S will be 2. I do the same thing for S equals 1, S equals 2, S equals 3, and you already see why I'm saying, well, this feels unnatural, but this is a direct translation of this DRN format into a Prism format. One thing where you can already see that you can be more concise is that we can say, whenever S is bigger than 6, that means that we're actually in one of those states at the bottom. Then with probability 1, the next state will be the same state where we currently are. So we're just adding self loops here. And so here you already start seeing the power of a more symbolic programmatic representation of these Markov chains. And then we can label some states by giving a proposition where this which states should be labeled with this label out1. Well, state 7 is to be encoding the outcome 1. Is this roughly clear? Because otherwise the next step will be very difficult to follow. Okay, let me continue. If you feel like it wasn't clear after all, please do feel free to ask me to go back to this, right? So here's a more formal introduction that I included, but I actually want to immediately go first to the example, and then I can go back to the formal definition. Here is a Prism file now for a grid. So think about a robot that is in an n times n grid. Right, we're a very discrete, simple abstraction of the world, and the own position of this robot is given by now 2 variables, the x variable and the y variable. And we have the 4 actions that correspond to taking cardinal directions. Now, how does this look like in a Prism format? We're now providing an MDP. We're saying, well, there is this constant integer n, which tells you the size of the grid. And now the x and the y variable, they range from value 0 to n. And initially, the value of x should be 3. Y is initially between 0 and n, and initially you're in 3. So we're creating an m times n grid, and we're saying your robot starts in cell 3, 3. This model doesn't make sense if n is actually less than 3. So there's a couple of additional checks that you actually would want to do, but I wanted to keep this as small as possible here. And then we are providing these 4 different actions. So, sorry. If you go north, then you can only go north in this encoding if the x variable is actually bigger than 1. And if that is true, then in the next step, then with probability 90%, we're actually decreasing x by 1. So that means that we're going up in my coordinate system. And with probability 0.1, the action will not have any effect. This is a typical thing that's called the slippery grid world. So your actions might not have an effect on the system. And we do the same thing for going south. So south means increasing x, going west means decreasing y, and going east means increasing y. And the actions that are available are always given just by the cards on the left. Now, I hope that you can see that this easily is very simple to create in many scenarios. And this is the preferred way of interacting with a model checker. So in order to show you how you now use Storm, we can again use call Storm, and we now need to provide what value of n we want to use. So if I run this, then actually on the back end within almost instantly, but not completely instantly, we've translated this into an explicit matrix that is storing all the transitions. So there's 30 states and a different number of choices and transitions there. If you want to understand this, so 6 makes sense, right? 36 times 6 times 6 is 36 states. So indeed, if I now change n maybe to 10, then you get 100 states. I invite you to try this with bigger values. I will also do that later in this session, if time permits. But this is how you can now use this Prism grid. Now we want to understand maybe a model checking question. So what do we want to do? We want to find a policy or a controller, a scheduler, whatever name you want to give to this, that minimizes the time until we eventually reach the corner where y and x are both n. And if you do this, then you would, and we want to do this for a slightly more interesting grid. So this is a 60 times 60 grid. And then you see that the result is that in 134 steps, on average, you can get to this corner. And we compute that almost instantly. One thing that is interesting also in the light of what was been discussed earlier, for these symbolic formats, it's a classical thing that the time for model construction is actually larger than the time for model checking. That also means that sometimes if you already have the sparse matrix, please don't first translate this into a symbolic format and then feed it into a model checker, right? That's not going to be efficient. On the other hand, we do spend significant effort in order to make these model checkers fast for the symbolic inputs. But there's quite some overhead in actually building the state space here. Now, there's some more advanced properties. Many of these you've already seen with Joost-Pieter. So what I first am going to do is I'm going to change the Prism format. We had a very small file. I'm now making it slightly bigger by adding some additional labels. So I say there's a station on 1, and there's a castle on 1, n-1. And on some cells, we have a different type of underground called grass. And that is true whenever either y is 3 or x is 2. And now I also provide movement costs. So now I'm saying when you're moving on grass, it takes you twice as much energy or whatever unit of movement you want to use than whenever you're not on grass. Then it costs you 1 unit of resource. And now we can ask maybe a question like, what is the maximal probability to reach the castle while spending not more than 40 units of resource here? So we're trying to find a policy that maximizes the probability that we actually reach the castle, but we cannot use more than 40 units of energy. If you do this, the outcome will be that within that there is actually a probability of 90% or 91% to do so. And you can have fun with this in order to ask different things, right? We in the presentation, Joost-Pieter did look at LTL properties. So here's an LTL property which informally says, make sure that you infinitely often go to the station and that you infinitely often go to the castle. And well, there is a we're asking, what's the maximal probability that some policy does this? And there's actually a policy that does this with probability 1. Here's a different question. For example, we can ask, is it possible that we reach the station within 7 steps and that we reach the castle within 7 steps? The answer is, well, that's only possible with policy. The optimal policy for this thing does this with probability 42%. And here I'm asking independently, what's the maximal probability to reach the station with in 7 steps? And independently, what's the maximal probability, so with a different policy, to reach the castle within 7 steps? And you can see that actually reaching either of those two within 7 steps is easily to obtain with very high probability, right? So that also highlights the difference between these properties. Now, I hope you're already thinking trade-off policies, right? So is there a Pareto curve here? Yes, let me come to that later. Okay. But one thing that is very unsatisfying about what I've been telling you so far is I'm telling you, yes, there is a policy, but I'm not telling you what that policy looks like, right? So policies and model checking speak are often called schedulers. So that's why some of these commands use schedulers. And now what I'm adding here is an option to say, please export the scheduler. And I call that plain sched. If you do this, you get a very long warning, which says, well, we didn't really include any information about these states. What does that mean? If we look at the scheduler, it's going to tell you in model state 0, take choice 3. In model state 1, take choice 3. Well, these model states refer to the places in the matrix, but we didn't provide the matrix, right? We only provided this prism file. So this is hard to use. Instead, what we suggest to do is we can tell the model checker to annotate all these states with information and also all the actions with information that reflect to the prism file. That induces a little bit of overhead. That's why we are not doing this by default. But if we do that, then you get an output which is much easier to interpret. It's, for example, it says if you're in XY, please take this choice 3, which reflects the east action. Right, and then I hope that this is a type of a scheduler that you can easily interpret. Okay, so let me briefly talk about this question because as it came up, there are different ways of working with Storm and the different backends. So far, as you've seen, we've been using floating point arithmetic. This is very natural somehow. But we've seen that in particular for high reliability concerns, if you want to show that you can reach that your system has a 6/9 reliability, then floating point issues might occur, right? Or if you want to show that the probability is smaller than once every 10 years or something like that, we're getting into very small probabilities. And using floating points is no longer a good idea. So Storm can also compute with rational numbers. Here was the previous Knuth-Jao die where we asked about the probability. The probability was 1/6. And here I can actually now ask Storm, can you do this exactly? And the answer is then indeed that the probability is exactly 1/6. Now, Joost-Pieter also alluded to this thing that, for example, MDPs can be checked with as a linear program. This is implemented in Storm. So here you see a method where we explicitly say when you're solving MDPs, and you do need to look a little bit into the documentation to understand that this is this min-max method that you need to set. I do understand that that might be hard to find, but we're working on this. Then if you say this is an LP, we can solve this. The answer is 7.22 and we take 7 seconds. That all looks fine. But if I now say a value iteration for the same problem, then you can see the difference in time. And so this is one of these arguments where value iteration is really lots and lots faster than linear programming. Now, don't be fooled. There is a good reason that we implemented LP types of solving. There are a few models where doing this with LP solving is much faster than using a VI. Typically, and also the standard way, if you do not tell which method to use, we will be using a VI. But sometimes for expert users, these are important features. And there's a lot of things you can do with Storm. Okay, I don't want to go into further things like you can use different sparse matrix representations. There's a little bit of information in the slides, and I'm happy to talk about this afterwards. So let me go over that. And there's also a hands-on session in the second part of the talk where I will continue basically where I left off. But I want to briefly show you the benefits of the Python interface. So let me first show you, if you want to use the Python interface, you need to import StormPy. And then you can, for example, print which version of StormPy and Storm you are using. This particular notebook has been initialized with these versions. And then you can say, well, please, StormPy, you now need to provide a little bit more. You're paying a price for doing this programmatically, but now you will get some benefits of the programmatic access to the API. So here we are now asking Storm, please parse the Prism program that you saw and define the constant n to be equals 6. And this program has two other constants, p and q, that will be useful later, that I'm now also initializing with some values. If you look at what we're doing in the command line, you also were providing a program, we were defining these constants, we're doing the same things. Now we tell Storm that we're going to build this thing and we're going to set some options. I'm not going to go into all the arguments here, but for example, here you now can say, I explicitly would like to build this with state valuations and choice labels in order to label all the states with high-level information. And then you can ask Storm to build this model using the options that you provided. And this will build this model and label all the states. So there's again a castle and a station. There's always an initial state, and this deadlock state does always exist, but it might actually not actually be true in any of these states. And now if you also want to run a model checking query, you can parse a property like before, and you can do you can call the high-level model checking API, and that will just then provide you with the result here. So far, that's very similar to what you would have done with the command line. I want to show you one thing where the trade-off analysis, in the trade-off analysis, and then after the break, I'll towards the end of the presentation, we'll do a thing where you really see the benefits of a programmatic access. So here we're now using a utility for multi-objective plotting. What are we doing? We're providing a property, and this property now says what's the maximal probability to reach the castle within 11 steps as a trade-off. So this is a multi-objective query. With also considering what is the maximum probability to reach the station within 8 steps. You can model check that. And as Joost-Pieter explained before, what we're actually doing is we're approximating the true Pareto curve with the under approximation and the over approximation. So in this result, you can actually now ask for the under approximation and you can ask for these vertices. These are a number of two-dimensional points, which, for example, mean you can reach the castle within 11 steps with a probability of 1, but then you will only reach the station with within 8 steps with a probability of 0.5. And on the other hand, if you try to optimize only going to the station, then you will reach that with roughly 85% probability, while only reaching the castle with a 26% probability. Now, of course, if you're already in Python, why not plot this? So indeed, we can plot this, and now you see exactly these vertices plotted. I'm also plotting the over approximation, and you can see that what we're actually providing, at least in this instance, is absolutely tight. So there is, strictly speaking, a wide area in between here, but it's not actually visible in the system.
Okay, I hope you can see my slides. Unfortunately, I cannot see my pointer, as somebody already noticed during the first part, so I will not use it further on. I'm not sure where it is actually at the moment, but anyway. Okay, so we have seen Markov chains, MDPs, how to deal with that with Storm and so on. Now I would like to give you an insight in one of the input formalisms that Sebastian was mentioning. These are fault trees. And we did quite some research over the last couple of years on basically applying probabilistic model checking to fault tree analysis. So fault tree analysis is used in reliability, and reliability, of course, is essential in all kind of safety critical, let's say, applications. I mean, planes, satellites, but also a kind of infrastructure. I mean, critical infrastructures like a water management system, or trains, or autonomous cars, or nuclear power plants. So in the field of reliability engineering, people have, it's all about analyzing risks, right? So it's about what is the probability that, for instance, in the power supply of the nuclear power plant, the power supply will break. And people have developed in the 1950s already developed fault trees for this. And this is one of the most prominent techniques in that field. It's used by a wide range of industries in I would say, very different application fields. And it's also used in standardization organizations like the FAA, the Federal Aviation Authority, which actually determines what are the kind of standard techniques that people have to use in let's say, aeroplanes. And in industrial standards like ISO 26262, but also IEC standards, they actually not only, let's say, recommend these kind of techniques, but even sometimes even require these kind of techniques. So I like this quote by Elon Musk. I mean, it was one of the endeavors by SpaceX. I'm saying one of them because recently we saw another one that exploded too early. In 2015, he sent a tweet around where it basically says, well, there was an overpressure event. Data suggests some counterintuitive cause, and that's all we can say with confidence right now. What we have to do is we would like to do a thorough fault tree analysis. So even Musk is using these kind of fault trees. So they have been defined, early 1960s, not the 50s, by Watson. So what is a fault tree? It's basically a directed acyclic graph. And it models a kind of gates, like in a logical circuit. So you have things like AND gates, and you should read them from the bottom to the top. So the AND gate will fail if both its inputs, which are below, they fail, then the output will fail. Similarly, you have OR nodes, or you have K out of N, which means if K out of N inputs fail, then the gate will fail, and so forth. And what does it model? Such a directed acyclic graph, they have events, which are the leaves, so to speak, in the graph, and they are occurrences of failures of system components. And then you build your whole graph, and then you're interested in, basically, it's a rooted graph, so you're interested in the top level event, which is basically a failure of the root of the fault tree, and typically that's modeling a catastrophic system failure. And so here you see an example on the left. It's modeling something like a workstation system. So WS, it consists of two workstations, W1, W2. These two workstations have something like a power station, and they share, for instance, a memory. Yeah, and the memory consists of 3 modules, and the memory fails if 2 out of 3 modules have failed. Yeah, so there is some redundancy in the system. And then what you see is the complete system is modeled by this root of the directed acyclic graph. And then the question that people would typically like to answer is what is called reliability. What is the probability that your computer will fail within a certain amount of time? Okay, where do the probabilities come from? Well, the leaves, C1, PS, M1, M2, and so on, they are attached or associated with a probability distribution. And now you have to think about a continuous distribution that basically indicates what is the probability that these components will fail within a certain amount of time. Now, typically they are negative exponential, but there could also be other distributions like phase types or hyper-exponential or other kind of distributions. Now, the crucial thing in these fault trees is what they call a cut set. What is a cut set? A cut set is a set of components, so a set of, you would say, leaves in the graph, such that if those components have failed, then the whole system will fail. So then the root will fail. And then you're interested in a minimal cut set because that's a cut set that is minimal in the sense that no proper subset of it will also lead to a system failure. So you see, for instance, in dark blue, you see in the left indicated this B, and this B is a child of an OR state or OR gate C. So that means C will fail, and that means the whole system will fail if B fails. That's minimal. In the middle, you see an example which is not minimal. It's a cut set because if all the 3 memory modules will fail, M1 up to M3, then the system will fail. But it's enough if 2 out of 3 will fail, so this is not minimal. And that's what you see on the right. So there you 2 have failed, and then you have minimal. Good. So the analysis of static fault trees is all about finding those minimal cut sets. So how do people do this? In a nutshell, you take such a static fault tree. You see an example on the left with the colored leaves. And then what you basically do, you turn this into a propositional logic formula because you have AND and OR gates and so on, and you encode it as a binary decision diagram. And you see 2 of those binary decision diagrams on the right, in B and in C, in figure B and figure C. And what's the difference? Well, we have seen or discussed already the order in which you generate your state space. Here is basically on how do you generate, so how do you traverse your directed acyclic graph on the left, and what's the order of doing this in order to get this BDD. So number B is basically obtained by doing a depth first search through the graph, and the right one is basically top down, left right. That's what TDLR stands for, and that's the order that you get. And you see, and as we all know with BDDs, the order, the size of the BDD is extremely sensitive to the order. So you see that the one on the right is a bit smaller. And now what you can do, you can calculate those minimal cut sets. You can calculate the mean time to fail. So what's the expected time that you need in order that the root of the tree fails? Reliability, what's the probability that your root will fail within a certain deadline? You can all do this using analysis on BDDs. Good. This is also in Storm. So here you see an example of some static fault trees. The table tells you the number of BEs. BE stands for the number of leaves in the graph, and the number of gates are the number of AND, OR, and voting gates, these K out of N gates. And you see different examples, Aurelia sprinkler system, which is a fire sprinkler system in a supermarket, something in a railway, and so forth. And this has been implemented in Storm, and we compared this to standard off-the-shelf techniques, tools for analyzing static fault trees. And 2 of them are Scram and XFTA. And here you see those scatter plots again. So these are log scale plots. Storm is on the y-axis, and at any point on the diagonal means that Storm is competitive to Scram. Any dot or any point below the diagonal means this is good for Storm. Any point above the diagonal means Storm is a bit slower, and it's log scale, so the dashed lines means really a factor 10 or a factor 100. Yeah, that's what you should see. So the bottom line of this is that Storm is competitive, but if they are large SFTs, and then you see that the more the curves in the X dimension go to the right, the more time it needs, then actually we are performing very well. Good. Now, people in the literature saw these static fault trees from the 1960s. Well, they're a bit simple. Yeah, you only have AND and OR gates. You can only model simple scenarios. What you can not model is something like spare management. Think about your car. You have 4 tires, but of course you always have a spare tire. So if one of the components, one of your tires fails, you have a spare and you can replace one of the tires with one of the spares. This you cannot model by static fault trees. Redundancies you can model to a certain extent, but not, completely. And one of the things you also cannot model are things what are called common cause failures. You have a kind of a cause which is common to many different failures that can occur in your system. There's no temporal ordering of faults and so on and so forth. So in the literature, there have been developed many different variations. And the one that we are going to look at are the dynamic fault trees developed by Johan Dugan. So this is Johan Dugan. She received the IEEE Reliability Society Award in 2000 for her seminal work on dynamic fault trees. because dynamic fault trees have extended the state of the art and the state of practice in analyzing the dependability of computer systems. Good. So let me explain those dynamic fault trees by a very simple example. Here you see a kind of, we would like to have a virtual meeting. And for your virtual meeting, you have some software, Zoom, Teams, or WebEx. You have internet, your Wi-Fi or mobile, and you have a laptop that consists of a couple of components. Good. So what you can do in a dynamic fault tree, you can have a kind of a spare. So this model over on the right, it means basically that if your plug will fail, so your electricity goes down, then you can maybe have a replacement by having an accu or a battery that you can use for powering your system. So if the plug fails, you replace it by the battery. Here you see another scenario where you can use such a spare. If the Wi-Fi fails, you can have as a backup, you can use your mobile phone. Yeah. Then you can have things like common cause failures. If your electricity goes down, then this means that your Wi-Fi collapses as well as your plug doesn't work anymore. So here you see that the electricity collapsing is a common cause failure for the both components failing. And then there is ordering. So this is what they call a priority AND. It's an AND, but now the order in which the children fail is of importance. They should fail from left to right. So this means your mobile will fail if first your prepaid is empty and then you reach your data limit. If it's the other way around, if your data limit reaches first, then your mobile will not fail because you still have some prepaid stuff over there. Now, these dynamic fault trees have been developed and they have been used extensively. They have been developed in the 1980s. And yeah, what people showed is that it's not suffice anymore to analyze these minimal cut sets. So this efficient BDD analysis that works for static fault trees is no longer applicable. And one of the reasons for this is that the order in which certain components fail is essential. So the typical way to do this is you actually compile or translate such a fault tree into a stochastic process. And typically this is a continuous time Markov chain. And if you model certain other phenomena, it can also be something with non-determinism, but let's not talk about this right now. Let's assume that it's a continuous time Markov chain. There are also people worked on Bayesian networks or Petri nets, but we will concentrate on continuous time Markov chains. And then what you can do, you can use Markov chain analysis to obtain the mean time to failure, the probability that the root will fail within a certain amount of time, and so forth. Good. So what Dugan already mentioned when she introduced these DFTs, that the construction of the Markov model for even the simple system is tedious and error prone. Good. And one of the issues that can happen is easily, well, you have to be very careful on how the state space looks like, but in particular, the state space can explode very quickly. So actually, Dugan developed this a kind of fictitious system of a DFT. And you see in particular, the number of leaves is, well, I would say, well, not substantial, but moderate. And they introduced this because, the corresponding Markov chain of this tree will be drastically large and practically impossible to solve without making any simplifying assumptions. So making a kind of abstractions or introducing some approximations. And indeed, if you do a naive state space generation, you get about 66,000 states for this thing. And Storm uses without any, in a naive way, 1 second to generate this state space. And of course, I mean, computers have made things faster over the last couple of years, but in particular, you can also make kind of optimizations. And this is what we worked on quite a lot in the last, I would say, almost a decade to optimize state space generation for these kind of models. So now if you run Storm on this example, it's in a split second. This is actually analyzed. And actually, you get exact results. So no approximations, no abstractions. What's the secret? The secret is the following. So what we do is similar as to model checking. We have a model and we have a specification. The specification is at the bottom. So this is something like a reliability or an unreliability measure. The probability that within a certain amount of time t, the system will fail That's the kind of the property, the typical property that you would like to analyze. But other properties could be the mean time to failure. And you can, of course, also model costs. So if you, let's say, think that certain components are expensive and you would like to say basically in your fault tree, you would also like to take the price of the components into account, and you can also model things with rewards as we have seen before the break. And then on the left, on the top, you see this DFT. And what we do is we're first going to simplify this, that gives you a simplified DFT. You can think about this as, you take a logical formula, a static fault tree, and you simplify this by logical rewriting. Well, here it's more complicated because, as we have seen, those dynamic fault trees ordering is important, but for instance, also the state is important. Which parts have been failed already and in which order. So it's not that completely trivial, but we developed some of those rewrite rules and they have been implemented. Then we actually analyze these DFTs, so we generate them efficiently. So we have very slim state space generations. We look at certain parts of the fault tree that don't care because they're not relevant anymore. And we do things like symmetry reductions. So that gives rise to hopefully a very small model. And this is what is indicated there with MA. And MA stands basically for a continuous time Markov chain that in, I would say, very special cases may also have non-determinism. But as I said, let's ignore this for the moment. And then what we do is we use, in the end, Storm to analyze this. Now, the main difference with the material we presented before the coffee break is that now we look at continuous time Markov chains. So no longer discrete, but now we really talk about continuous distributions. Good, so we look at many different optimizations. I will not go, I will be a bit quicker here. We use don't care analysis. So here you see, for instance, this example, this green element says it only fails if C fails before D. Now, in this scenario, you see D has failed, indicated with red. So it means this element P can never fail again because C has not failed yet. So that element becomes what we call fail safe. That's the color green. But that means that now, for us, this component indicated with C is no longer relevant because it will never lead to a failure anymore. So in our state space generation, we exploit this. And I mean, you can even think about C being an entire subtree, and we basically completely ignore this subtree then. Then we can look at things like symmetries, and symmetries not in terms of the Markov chain, but in terms of the graph. So here, if you see that A, and again, this could be a whole subtree, if A is isomorphic to B, then you can exploit this in the state space generation. And that means that only you have to can do then a much more efficient state space generation. And then there are things like modularization. That sometimes means that you can split subtrees. You can evaluate those subtrees independently and then use the results to analyze the rest of the subtree. So this is also something you can use. And then you can do other tricks like eliminate if there is non-determinism. If it's spurious, spurious means no matter how you resolve the non-determinism, the result will be the same. We do this rewriting before the analysis, as I mentioned before. And actually, we can also do a partial state space generation. Good. So all these techniques we revised, we improved and extended them over the years. And this has led to basically analyzing those fault trees in Storm. So we used a benchmark suite, which is publicly available at the website, which is at the top, where the main focus is on computing this unreliability, so the probability to fail within a certain deadline, and this mean time to failure. There are almost 400 benchmarks, and we compare this to two tools. One tool that does simulation, and that tool is in particular good if there are what is called rare events. That means events that happen with a very, very low probability. That's what it's the name RES stands for rare event simulation. And then there was a tool developed in 2013 that uses a compositional technique to generate state spaces. And that's why we compete with. And this is how it looks. And again, kind of a quantile plot we have seen before the break. The number of solved benchmarks on the x-axis And on the y-axis, log scale, again, the time in seconds to resolve this. And you see that, thanks to all these kind of optimizations, part of them existed in the literature, part of them extended, part of them they were developed by us. We were actually, I think it's fair to say that that Storm is, let's say, at the moment, by far the fastest and most scalable analysis tool for fault trees. Good. And the slogan here is that Storm solves more benchmarks in 1 second than others in 1 hour. I would like to explain you one technique that we developed that is actually intuitively quite easy to understand, but turns out to be rather effective. And this is what we call a partial state space generation. So you take a fault tree on the left top, and you take your specification on the middle, on the top of the slide. And now what we do is, rather than generating the state space completely, we first do only a partial state space generation. Good. And now we basically take a very conservative view and a very optimistic view. So we only partially generated the state space. That means we did not cover certain fragments of the fault tree. Now, what would be a worst case assumption? The worst case assumption is those parts that you did not see yet, they will all fail immediately. Now, that would be the worst case. What would be an optimistic view? An optimistic view would be all parts that we did not consider yet, they will never fail. So what do we get? We get an optimistic and a very pessimistic view, and that gives us an upper bound and a lower bound. That is what we analyze. Now, in this case, you could have something like a lower bound is with 0.20 and an upper bound that would be 0.21. That is very good, and that could be precise enough, and then you could stop. If it's not precise enough, and I will have an example in a minute, then what we're going to do, we're going to expand the partial state space. And actually, we repeat the whole process until we will be precise enough. So how does it look like? So here you have a fault tree, a very toy example on the left. There is an OR gate in the top, E is an AND gate, and this P is this priority AND. Remember, the priority AND says it can only fail if C fails before D. Now, what do? We generate the state space. How does that look like? Well, it looks like a kind of this continuous time Markov chain on the right. It's a continuous time Markov chain because these alpha, all these Greek symbols, they are rates of exponential distributions. So they model continuous time distributions. We start in a state where nothing has failed. That's the left state. And then, of course, what can fail? Well, one of the children can fail. So that's what the output alpha, beta, gamma, delta will interpret. And let's suppose that, for instance, alpha fails, so A fails. Then what can happen? Then of course, B can fail, right? Or one of the other children. So there you see the outflow of 3 and so on. Good. This is a partial state space. Now what we can do is we can analyze this partial state space. So we can say, well, take a very optimistic view or take a very pessimistic view. Pessimistic means everything that you did not explore becomes red, fails. Best case means everything that you did not explore, you just assume this will never fail, so it becomes green. Now you analyze both cases. So now you get, for instance, for the best case, the failure probability could be something like 0.023. And the worst case says, well, the failure probability is very high. It's almost 1, right? It's 0.974. This, of course, is not very satisfactory because the gap between the best case and the worst case is rather large. So what are we going to do? We're going to take our partial state space and we're going to explore this a bit further. How are we going to do that? We have effective heuristics that tell us where should we explore this a bit further. So you see that here we explore this a bit further by looking at the red circled states in the picture in the middle, the one that you reach from the initial state by doing either a beta or a delta. And what we do is we explore those states a bit further. We did this here only for one step. So you basically look at what are the possible outgoing edges of the two states that are circled with this red circle. And this gives you the picture on the right. This gives you, again, another partial state space. Notice that some things have changed, some edges have added, And now what we can do is we can again analyze the best and the worst case, and you see that the unreliability and is basically the difference between the lower, the best case, and the worst case probabilities have been lowered to 0.145 and 0.535. Good. And this you can continue until you are, let's say, precise enough. Good. And this technique, together with all the optimization techniques, are available. And I would like to spend the last part of my talk by showing you 3 applications. One from railway industry, one from autonomous cars, and one in the area of nuclear power plants. So I would say energy. Good. And this is the first example is about a criticality assessment of railway station areas. So what did we do here? Well, there are standard notations in which, let's say, railway engineers, let's say, model the infrastructure in a railway station. And here you see an example of such a thing. And you see all kind of equipment. You see switchings that are there. You see signals, tracks with holding positions, axle counters that you need in order to release certain routes, and so on. Good. What are we interested in? We're interested in routing trains through a railway station. So in order to do that, you need to set a train path. And you see this partially already here in red. This is a partial train path through the railway station. Good. Then we have the different field elements, those signals, those switches, those axle counters, and so on. They must be operational. And of course, like switches and so on, they must be in the correct position. Good. So what was the approach we took? We took as input these infrastructure data. So we literally took those data that, for instance, Deutsche Bahn has as its availability. And for that, we developed basically fault trees for the different possible train routes and for the different field elements. So we looked at what is the reliability, what is known in the literature, what is known from the experts on those different components, and they were modeled in fault trees. And then from that, we basically compiled, so we basically combined the fault trees for the station and the fault trees for those field elements automatically by generating a complete fault tree for that particular station. And that we feed into Storm, and then we analyze that using the techniques I just mentioned. So we simplify this DFT, we maybe use partial state space generation if needed, and so on. Good, so here is an example of such a station fault tree. We have a station, you have different routes. These are those the second level of the tree. A route set consists of a route 1 and a route 2, and then you have a train paths, which are those different colors in the bottom, a red, a green, and a yellow one. Yeah, so here you have, for instance, a plan. Then you, for instance, have this red path thing. This is the red train path on the left. You have continuation in the green thing. That's the subtree, which is rooted at the green child. And you have a yellow path, which is basically the path rooted at the yellow child. So in this way, you model such a station. You can imagine that for a real station, those models can be large, and we will see some examples in a minute. Then we looked at the different field elements. So slip switches, crossings, track clearance detection, and so on. We are not experts in railway engineering, right? So we did this together with actually experts here in transport engineering at RWTH Aachen. And they were very useful in order to provide us all this information about these field elements. And also to provide us information about what is, let's say, what are adequate models. When do those slip switches fail, right? What is the failure model of crossing? Is there any practical data for this? And can we use this? And that's what we did. We combined data from different countries, actually, Netherlands, Norway, UK, because, I mean, experts, I mean, in particular, companies that are, whose task it is to, let's say, monitor these kind of equipment. They're very reluctant to give us this data, but luckily in the literature, there were those data quite available. And now what we do, we looked at the criticality assessment of railway infrastructures. So here you see a picture, I think this is Aachen Hauptbahnhof on the right. And here you see on the left, you see Mönchengladbach some time ago, a very old picture of this. So we looked at several stations, Aachen, Herzogenrath, which is basically here in the area, and for instance, Mönchengladbach, different variations. Number of route sets, you see that Aachen is a bit larger than Mönchengladbach, for instance, the number of routes you have, the number of train paths and the number of components. The number of components are the number of field elements in this railway station. And if you model this now as a fault tree, here are some statistics about the size of these fault trees. Well, they roughly have about 400 to 500 children, the number of basic events, second column. The number of static elements in the fault tree, so these are ends and ores and so on. This is about ranging between 150 to 500 almost. And the number of dynamic elements, so these were those spare gates, these functional dependencies that we use to model common cause failures, but also, let's say, panned gates, these priority ends. These were roughly ranging between 20 and 50. And now if you generate the state space, if you now look at what is the size of the stochastic process that you need to analyze, this is the statistics in the, let's say, the 3 columns in the bottom left table, the number of states, number of transitions, and you see also the amount of time in seconds that Storm needs to build these models. So you see, for instance, that for this model of 11 million states and 45 million transitions, which is the largest scenario of Aachen railway station, this took about 2,000 seconds to build this model. And similarly for this model of Herzogenrath with 17 million states, this took about 1,000 seconds. These fault trees were automatically generated in the sense that, we have these fault trees for the different, let's say, we looked at the topology and there we looked at the train routes, and we have those DFTs, those fault trees for the different elements, field elements in the station. And also these Markov chains were automatically generated. So what we built is really a tool that takes as input, a diagram, this kind of input, a kind of topology of the railway station, and the output was a kind of a temperature plot, and you see an example here that indicates immediately to the railway engineers what are the most critical elements in your railway system. And the more red these elements are, the more critical. Now, it's not surprising that these critical elements are, for instance, on the left, because there are the two railway entrances of the railway station. So, of course, if those will fail, that will be highly critical. The same completely on the right. But for other elements, we were able to analyze the criticality using this fault tree analysis. And actually, we're even able, and here you see a more detailed thing, that we even look at switches, and you can even look at do you come from the left and do you go to the right, or do you come from the left and you go down, for instance? Does it make then a difference how critical these are? And these were the kind of, in terms of jargon of fault trees, this here, what you compute is basically the sensitivity. You can think about the sensitivity of those switches, and this is called the Birnbaum importance index for those branches. As a second example, I would like to refer to an industrial case study we did with BMW, and this is about autonomous vehicle guidance. For those autonomous vehicle, there are those ISO standards 26262, and they define different automotive safety and integrity levels. And here we're going to talk about level D, and that's one of the, levels in which the number of residual hardware failures per hour needs to be extremely low, 10 to the power minus 8. So this is highly safety critical. What BMW provided us were basically functional safety blocks. So here you see some of them, 4 of them at the top. So here you see something like, an environment sensors on the left. You see some planning control. These are these EPs and TPs, and you see actuators on the right, which are those A1s up to AK. And now you can have different models with different types of redundancy. So in a nominal function, you have one module called this environment perception, and one trajectory planning, and one actuator management. But for instance, in B, you see that there are, 3 redundant entries, which means if one of them basically fails, you still have 2 functional ones left. So that, of course, is more reliable. And then you have different kind of other scenarios where you have fallbacks and so on with different, let's say, safety levels. But as I said, I'm not have the time to go in all the details here. Then they gave us examples of car architectures. So here you see an architecture on the left with one bus where you have one ADAS, which is an advanced driver assistance system, and different integration ECUs that are connected via a bus. In the second one, you see two buses with basically 3 different modules of ADAS, so that's again more reliable. And here you see on the right, you see, for instance, something where the ADAS is doubled, and this ADAS plus means this is a more reliable version of ADAS. Good. And what basically BMW was interested in was the following question. Now we have different, let's say, functions that are the uppermost 4 pictures that model the different kind of software or hardware modules that you have in your system. And you have basically architectures of your system, which were the 3 scenarios at the bottom. What are the best possible mappings that you can make so that your system is mostly reliable? That was the question, yeah, I would say, put in a nutshell that BMW was confronted with. So we looked at different metrics. So the obvious metric is something like how probable is it that the system is still functional at some point in time? But more interesting is, for instance, the question number 3. If the model gets into a degraded mode, so some components have failed, what is then the expected time to failure after that the system becomes degraded? Yeah. Or system integrity, that means, for instance, you limit the amount of time that your system is operational after degradation. Degradation, can you then still say something about what's the probability that your system, that your car is still safely operating? Good. Here you look at, again, and I'm referring to the blue columns in this diagram. We looked at different scenarios. We looked at different dynamic fault trees. So the experts by BMW gave us all kind of information about these different components, the ADAS, the sensors, the actuators, the fail behavior, and so on. Storm automatically generates these stochastic, these CTMCs. Some of them are relatively small, a few hundred, a few thousand states, but we also have larger ones where you basically have 400,000, almost 500,000 of states with numbers of transitions. And the last column indicates the percentage of the states that are actually representing the degraded mode in your system. And what we did is we analyzed the system for BMW for different system scenarios. So for instance, if you look at the plot on the left, you see the amount of time on the x-axis and the failure probability on the y-axis. And we looked for different scenarios. So for different, let's say, mappings of the functional architecture to their basically system architecture. And this was all done with Storm. The last example is an example we did together with Électricité de France, which is the largest energy provider in France. So we looked at a nuclear reactor that was managed by EDF. And in particular, we looked at the emergency power supply of this nuclear reactor. And there, different metrics were considered, like reliability, mean time to failure, and so on. Now, this system was presented in a paper by Boujou in 2017 as a challenge. Basically, EDF was presenting this as, here we have a challenge. This is a complex system because there are multiple power sources. There's a large difference between the failure rates of the components. This means that if you use iterative techniques to solve this, convergence is an issue, or you maybe want to do rare event simulation because you have events occurring with a very low probability. There are common cause failures, and so on. So we modeled this, here you have a kind of architecture of the system. I do not go into the details here, but just to make clear, we're not modeling the plant itself, we're modeling the power supply of the plant. And here you see that, for instance, different components of this redundant power sources in this power supply. Good. And the aim was to analyze what is the probability that the power supply completely collapses, and that, of course, would be a catastrophe. So we modeled this as a dynamic fault tree. So this looks like this, which is a rather complicated fault tree. Together with the experts of EDF, we checked whether this is an adequate, let's say, representation of the reality. This model has about 200 elements, a quarter of them being those dynamic gates. And here you see more statistics about this model. And although, it was clear that you cannot adequately model this by static fault trees, so you need to do something with dynamic fault trees. Actually, Électricité de France has their own dialect of dynamic fault trees, and later we also use them to analyze this case study. But for dynamic fault trees, we were able with Storm to solve this challenge after, in particular, using this partial state space generation in 14 seconds. And this has led to a commercialization. So actually there is this year a commercialization has been launched. The tool is called SAFEST. It's called the Static and Dynamic Fault Tree Analysis Tool. It's basically inside its Storm, but then let's say these slim state space generation techniques, the techniques to optimize, let's say to simplify, to rewrite fault trees. There is a graphical user interface in which you can draw fault trees and so on. So this is very user-friendly and built on top of Storm. This has been launched, and if you're interested, you can have a look at this link, which is here on the slide. So it both supports modeling. You can do modular modeling of DFTs, and it also supports analysis using Storm. So fault tree analysis with Storm, what I tried to mention is that you can analyze, very large, and we claim the largest fault trees ever. The metrics are the standard reliability measures, but you can also do much more complicated measures. Think about the kind of measures, the kind of specifications we mentioned before the coffee break. It's fully automated. First, there is a variation of Storm DFT, and now there is this commercialization in SAFEST, and it is validated by various industrial case studies. And how did you do this? I mean, we did this rewriting of fault trees, a slim state space generation, and we did this tailored Markov chain model checking. Good, and you can try it out yourself by looking at this SAFEST tool. And for EDF, actually, we also applied the same principles to a dialect that is dedicated to Électricité de France. It's called BDMPs, where we basically solve the same thing. We will make the slides available, and on the slides you will find much more, let's say, literature on what are the underlying techniques that I presented shortly in my presentation. Good. So far about the fault trees, but before handing over to Sebastian, I'm more than happy to answer any questions.
Maximilian.
Yeah, thanks for the talk. So I was wondering, when I was seeing the example from the railway, is like this process of like model specifications or like fault analysis somehow reversible? So like, because you're always given a model like of like the reverse of the railway system or something, and then you check if something is, if it fails with like a probability less than something. But like given like constraints of like numbers of platforms or numbers of rails or like numbers of junctions or like trains per hour, whatever, is like this process actually like reversible, that you then get the train like system, railway system that has this property? Like, you know what I mean?
Yeah, I guess you are referring to, so what we do is we do analysis, and this is a kind of a posteriori analysis, right? The input is such a plan of a railway area, and then we analyze. We not only answering is the probability larger than a half, we compute the exact probability up to a numerical accuracy or inaccuracy, right? What we don't do is we do not synthesize automatically what is the amount of redundancy that your system needs to have, such that the system satisfies a certain specification. That is a kind of a synthesis question. For these fault trees, we don't do this, but we have some work on analyzing, doing this for discrete probabilistic models, so Markov chains. And there you can think about, okay, you have a Markov chain, but you don't know the exact topology. You don't know exact the number of states, but assume it's finite. And now you give me a specification. Can we synthesize for which kind of Markov chains we can guarantee that the specification holds? And for those, we have some, this is an active research area, and we have a tool based on top of Storm. It's called Paint. And this is about synthesizing these kind of models. But that goes in the direction that you mentioned. Yeah. But it's fair to say that for fault trees, we did not do that yet.
All right. Thank you.
But very good question. Yeah. Yeah, because that would be great, right? I mean, then you turn the problem way around, right?
Yeah, exactly. You don't have to build everything beforehand and then check after. So.
So we're working on this. Yeah.
Like more questions? Doesn't seem to be the case.
Okay.
Sebastian, please.
Yes. So Maximilian's question was a great prelude to what is to come. Do you see my slides?
Yes, you can see them. I can see them.
Okay. Let's assume that generalize as well. We're going to talk about parametric Markov models.
Du bist jetzt auf, you're on mute.
Sorry. Okay. So Maximilian's question was a great prelude. I hope you can see my slides even after I unmuted myself. And I'll give you the take-home message right away. So we will look at parametric Markov chains, and these are Markov chains with unknown probabilities. So by the end of this talk, you will understand what these are and how to use them. In particular, you will understand what kind of questions you can ask about them and also what kind of things Storm can help you with. I will talk about different applications in control and parameter tuning that there are, and these applications, they're not on the industrial level that Joost-Pieter was just talking about in the fault trees, but still we've applied them to a variety of case studies and benchmarks from other domains. And similar ideas of what I'm going to talk about for parametric Markov chains also apply to families of Markov chains. And these families of Markov chains, you can really think in the spirit of Maximilian's question. So I give you a set of potential designs, and I'm asking a tool to come up with the best variant within this set of potential designs. So downside, you still have to come up with some ground rules, some set of potential designs, but then you can flip the question around, not ask what is the probability in them, but actually give me the best design. So I'll talk about concepts, encodings, and methods, which will be more on the theoretical side. And then we'll talk about POM-DP's parametric Bayesian networks and product lines in order to get a feeling for how do we use these techniques in application domains. So here's the Knufjau die again. I hope you remember it. We're still flipping coins in order to simulate a die. And in order to change my story slightly, we're now having two still fair coins, a blue coin and a green coin, and we're flipping them alternatingly. This does not change anything about the protocol. However, now assume that this blue coin is no longer fair. So it has a slight bias towards flipping tails. Then the probabilities of actually reaching one of these 6 outcomes is changed, and you can still analyze this, but it's not a priori clear how this is changing. And if now additionally the green coin also becomes unfair, in this case quite biased, well, you can of course recompute every probability, but now it's completely unclear whether this is still simulating something resembling a fair die. And so this leads to this idea of parametric Markov chains, where instead of talking about concrete fixed probabilities, you talk about symbolic probabilities. So there's the transition probabilities are now no longer fixed numbers, but they're actually polynomials over a set of parameters. And in this talk, unless I explicitly mention something else, we'll use x and 1 minus x and y and 1 minus y as parameters. This avoids some technical challenges. So here, what are we actually describing? We're describing a system where the blue coin flips heads with probability x. And if it does flip x with probability with heads x in this state, then also the same probability must occur when in this state S3 we're flipping the blue coin again. And now, in order to get back from a parametric Markov chain to a concrete Markov chain, we can replace these parameters by what we call an instantiation. So replacing x by 0.6 and y by 0.52. In every individual transition, we obtain a precise Markov chain again. So the typical question was, what is the probability to reach the red state, or is the probability above or below some threshold? And in order to answer that question, that now really depends on the parameter values, right? And this is not so easy to answer. So if I want to ask you, well, can you somehow maximize the probability to reach the red state in order to show that the probability to reach the red state will be above a half or something like that? You have to think a little bit, because in the first state, it's clear that you want to have x as large as possible. If x is very small, then most of the probability mass will go from S1 to S5, and from there, no probability mass can reach the red state. So x should be large. On the other hand, if x is large, then all the probability mass that actually reaches S4 will flow to this state with the outcome 2. And so the probability will be very low to reach the red state. So far, only looking at this transition and at this transition here, you would think, well, x should be roughly in the middle, and indeed it would be true. But then there's also this x. So if the probability mass in the green state flows to S3, then we want to go back. And that means that x should be as large as possible. But then, how big is this influence of this x? Well, that really depends on y. So this is a completely non-trivial question, even for a very small Markov chain. And that leads me directly to one of the fundamental problems that we're trying to decide here. Is we're given a parametric Markov chain with these parameters, and we want to find a value of these parameters such that after replacing the parameters with these values, the Markov chain satisfies any of the specifications that we've seen in the first parts of the tutorial today. And in particular, in this talk, let me just say we want to reach the red state with a probability that is at least or at most lambda. So there are various settings here that you could consider. For example, you could think about this parameter space partitioning, which means that we want to understand for every point of the parameters, does this actually satisfy the goal? So for parameters P and Q, we want to understand how a different variable for P and Q leads to satisfying or not satisfying a specification. On the other hand, sometimes all we want is really just to find a needle in the haystack, right? Give me one instantiation of this system such that we satisfy our system. And which setting we are changes this question a little bit, right? So sometimes we just want to find some valuation, and sometimes we want to find all valuations. Now, for different types of motivation, you also get into different kinds of questions. So the most traditional application of parametric models is in this uncontrollable parameter setting. So there's some environment, some network protocol where the probability that your packet reaches its destination is given by a stochastic process, or say by a parameter P. And we cannot control that parameter, right? We cannot change the reliability of the network protocol, but we have to work with it. And in those settings, we typically want to understand robustness. So we want to understand for all these probabilities or around a particular point, what happens if we change these parameters? How sensitive is our protocol against changing these environment parameters? There are also other types of motivation in the uncontrollable parameter case, but I today want to particularly go into this controllable parameter setting. And there we know that there are lots of randomized algorithms around to break symmetries in distributed protocols, for example. And a good question there is, what kind of probabilities should you use in your randomized algorithm? Right? So if I have a traditional backup algorithm in my network protocols, which avoids collisions, then I flip a coin and decide whether or not I should send a message. If I say, well, I wait a lot, right? With a high probability I wait, then the throughput of my system goes down. On the other hand, if I set the probability to actually send a message, then the probability for a collision goes up. And this is a trade-off, a different type of trade-off than the ones Joost-Pieter mentioned in the first part of the talk. But there we want to find good parameter valuations. You can also think of this in a more discrete setting or in the setting where you want to synthesize systems, right? So how should we configure any given system? What kind of components should we maybe use in a fault tree that have sufficient reliability in order to achieve an overall system quality? And you can think also of this as these probabilities within controllers. So I will talk about partially observable MDPs in a little bit, but Joost-Pieter earlier already had these policies in trade-off analysis where said, like, actually your policy also has some probabilities, and we can use parameter synthesis in order to find such probabilities. So I hope that gives you an idea of the concepts that we're talking about and the motivations that typically underlie these questions. And I want to give you a brief intuition on what's actually happening on the mathematical side here. So here's again the Knuth-Jauer die. And my question is going to be, does there exist a valuation of these parameters such that red state is reached with probability more than 1/6? This is a simple question. The answer is yes, but I want to show you the encoding in a natural way. So what am I asking? I'm going to ask whether there are values pi, just like in the linear equation system that Joost-Pieter showed you before, and whether there is a value for x and a value for y such that the following things hold. X and y should be strictly between 0 and 1. The cases where x are 0 or 1 are also interesting, but they require a slightly more elaborative encoding. And then what I can do is, as Joost-Pieter said before, the probability to reach the red state from the red state should be 1. From all the states where there is no path to actually reach the red state, the probability is definitely going to be 0, no matter the values for x and y. And then we can have this recursive linear equation system where the probability to reach the target from state 4 is x times the probability to reach the state from this outcome 2 times 1 minus x times the probability to reach the target from this red state. Can do the same kind of equations for all the other states here. And then in the end, I'm going to ask, is the probability from this initial state bigger than 1/6? Now, this is a linear equation system, but it's no longer a linear equation system over constant parameters, but rather over functions. So you could also think this is a nonlinear equation system that you're solving. It depends a little bit on your perspective. And the problem here is that this is an exact encoding of the problem, but solving nonlinear equation systems in general is a very hard problem and it doesn't scale. So in particular, if you put this into IBM opt or something, then IBM opt will already take a couple of seconds to answer this very simple question. And if I'm going to scale this to a couple of hundred parameters, there's states, even just with 2 parameters, there's no way that your off-the-shelf nonlinear equation solver will solve these questions. So as I said, solving system of polynomials in general is exponential in the number of variables, and the number of variables that we're using are the states and the parameters. Often there's maybe only one parameter that we find interesting, or two parameters. And the number of states can be very large. So lots of people consider this question, can we do something that's maybe bad in the number of parameters, but that's worthwhile in the number of states? And yes, because you can eliminate these state variables. If you think of this as a linear equation system, you can apply a variant of Gaussian elimination. And what you will obtain is a rational function, so a fraction of two polynomials over these parameters that encodes the probability to reach the red state. So in particular, in this Knuth-Jao die, the probability to reach the red state here will be x times 1 minus x times this fraction. This is the precise probability to reach the red state. Now, if you change x and y, you will get different values, which is the same as if you would first change the parameters and then analyze the Markov chain. So lots of people invested this. There's some nice facts. So if you think about this for k parameters and n states, and all the transitions are assumed to be linear that you have as an input, then the rational function can be exponential in the number of parameters, even if this parametric Markov chain doesn't have any loops. And for any fixed number of parameters, the computation can actually be done in polynomial time in the number of states. So if you have only one or two states, parameters, you still have a polynomial time routine. Let me also give you the downside of this. Polynomial time does mean that it scales well, but it doesn't mean it runs fast. In particular, here is the result of doing state elimination on a 41 state Markov chain, which had 138 transitions. So it's a sparse system. And we do see here that the outcome is a function over two variables, x and y. But the coefficients that you get in here are tremendous. And you also saw that the function itself is huge. So sometimes this is a good idea, but more often than not, this is not going to be practical. So what we do instead is we provide more approximate solution techniques. So one of the standard questions that is typically asked is this exact partitioning, right? So can you give a region of parameter values and split it into those which satisfy a specification and those parameter values such that the Markov chain wouldn't satisfy the specification? Well, that's, again, not a very good question to ask, because that actually asks for finding this function, which is the solution function that I was just showing you. Well, for the Knuth-Jao die, you can actually plot this function, right? That's fine. But in general, you should not try to find that exactly. But we do instead, as we do, as shown in this picture, actually, an approximation of that. So you will get these rectangles in red and green that give you a nice approximation of the actual shape. So that also shows you a little bit of how we actually find sometimes all or some of these values. There are some more methods, and as I said, right, they need to be more efficient than computing the solution function. And they really are split depending on the question that you're asking. So if you care for all points, you can do variations of this encoding. You can be a bit smarter than actually just asking your nonlinear equation solver, but in the end, they will not scale very well. And then there are abstraction techniques that are helpful in order to provide these kind of plots that I'm actually showing you. They're based on a notion called abstraction refinement, and they have been heavily investigated. This is absolutely the state of the art, is to approximate these pictures if you want to care for all these points. And then you can go up to, say, 10 parameters or something like that. It depends, of course, all on your system, but 10 parameters and a million states is very reasonable there. On the other hand, if you only care for finding some satisfactory point, then we see two families of algorithms. One of them is based on sampling, right? guess a point, and then you just check whether that point using a regular model checker satisfies your specification or not. And if not, then you use the information from the point to guide your search. If you do this using particle swarm or gradient descent, that actually works well up to 100 parameters, right? But at some point you're searching in a very, very high dimensional space and it becomes very hard to do. On the other hand, there are iterative convex optimization schemes. So what they do, they take the nonlinear equation system and they convexify the system. So if you think convexify is a strange word, think linearize the system. So you guess a point, you linearize around it, and you use that in order to drive your search strategy. Well, if you compare these different approaches, then what you can say is if you actually use the solution function very on the right, you're exploiting the model structure a little bit, right? Because this function induces all the information. You can, in a one-shot manner, find a solution if you're able to actually solve the solution function, right? If you can actually solve this, the question whether that has a root, a value where this becomes 0 or 0.5. But this will not go beyond, say, 4 parameters and thousands of states. And then there in the middle, these iterative convexification strategies, they require a different amount of iterations, so they will actually need quite some time in actually to do the search. And here it depends a little bit. If you can save some iterations, but then every iteration is a bit more expensive, or you can actually try to have a faster iteration time, but then require more iterations. And there, what is nice here, we can really go up to thousands of parameters, which can be very helpful for some systems. And on the other hand, these sampling methods, they do not exploit any of the model structure. That means they need a lot of iterations in order to get somewhere. But then on the upside, what they're doing is just calling a model checker straight out of the box. That's going to be fast. And that also means that you can easily go to millions of states, but you cannot go to too many parameters. So there are a couple of out of the off-the-shelf techniques, but what kind of technique you want to use really depends on the number of states and parameters that you have, as well as all kinds of additional technology. And the question which of those techniques to use is still a little bit open. The default, what I personally always do is I start with this SCP thing, and if that does not work, then I shift into either of those directions. Okay. So here, in terms of type of presentation, there's a slight break. This is all I wanted to tell you about the methods and the underlying ideas, and I want to show you now a little bit on where do these parametric systems originate from, what do we do with them, how do we translate things in order to get to these parametric systems, and what can we solve with them. So here is a POMDP. The word has been mentioned a couple of times. The idea is that we have an MDP where we want to reach the red state without ever visiting the dragon. And in every cell, think about this as a grid world, you can go in either of the 4 cardinal directions. This is a very simple question to ask, right? If you're in state 6, you go up, and then you go right, you go down, you're done. Now, the problem is that you cannot observe whether you're actually in state 6, 7, or 8. And likewise, you cannot observe whether you're in state 2 and 4. You can think of this as a room. You're in a room, you see doors on the left and the right, but you don't know whether in which of those rooms you are. Now, if you start in 1 or 5, then you still have a positional policy to reach the red state. However, that positional policy does have to randomize in states 2 and 4. So what you would do is in state 1, you would go right. In state 2, you would flip a coin and then with some probability go right and with some probability go left. And then from state 3 onwards, you can just straightforwardly reach the target. Why do you have to randomize in state 2? Say you would in state 2 always go to the right, then that means that in state 4, because we're looking at positional policies, you would also always go to the right. And that, of course, means that if you actually are starting in state 5, you will never reach the target. Now, if you start in state 6 or 7, then there is no positional policy, because if we would say that we, with some probability, actually go down, then we would reach the dragon with some probability. We absolutely do not want to do so. So here you can no longer play positionally, and you actually have to store something. For example, the information whether you've been in state 3. So how does a policy then look like? The policy says in 6 or 7, you initially go up, and you try to reach this state 3. And then once you've visited state 3, you say, okay, now I switch my regime, and from now onwards, I will just go downwards if I'm status 7. Okay. How does this relate to parametric Markov chains? So you can think about these MDPs as having, as these POM-DPs as having states, and in every state you observe a color. And now the question in POM-DPs always is, if you have a POM-DP, if you have a sequence of colors, is there a policy that reaches some red state with a probability bigger than lambda? I know that there are some different variations of POM-DPs, but for this talk, really, please bear with me here. If this is the notion of an MDP, and we are looking at a positional policy, then what we're looking for is a mapping from colors to distributions over actions. Now, let me rephrase that. If we're mapping, instead of mapping colors to distributions over actions, what we're going to do is we're going to map a pair of an observation and an action to a probability. So for example, we're going to say if we are in the green state, then we are going to take action A1 with probability 1 minus x, and we're going to take action A2 with probability x. That's the same thing as actually defining some distribution over the actions when you are in the green state. In the blue state, we have 3 outgoing actions, A1, A2, A3. So here we're defining any distribution over actions A1, A2, A3. And that means that here we're saying with probability Y1, we're taking action A1, with probability A2, we're taking action, with probability Y2, we're taking action A2. And then with the remaining probability, we'll take action A3. So any positional strategy is uniquely described by the values for X, Y1, and Y2. And so we can actually apply such a policy and obtain a parametric Markov chain. So what are we doing here? So for example, in this green state down here, we're applying action A2 with probability X. And so with probability X, we'll actually return to the same state. And we'll apply action A1 with probability 1 minus x. And so with probability 1 minus x, we'll go up to state S2. In state S1, we're doing exactly the same. So with probability x, we'll take action A2. And that means that with probability a half times x, we'll reach this state on the left. And with the remaining probability, we'll reach state S2. You can do the same thing for the blue states in order to obtain this Markov chain. Now this Markov chain, parametric Markov chain, does no longer have this nice structure that I asked in the beginning with x's and 1 minus x, but you can translate this into a normal form quite straightforwardly. And so what is nice is that if you now have a POM-DP, you can and you want to find a policy, you can translate this into a parametric Markov chain, and you can ask for parameter values such that you satisfy your goal. If you say, well, I don't want a positional policy, but instead I want a policy that actually does have memory, that's fine, and you can still extend this method. Now you might argue, well, is this really a good idea? Yes, we've applied this to a benchmark on satellite navigation. And there what we're trying to do is satellite navigation. What you can think about is you're in an orbit and you want to navigate as few as possible, because every time you're changing your orbit, it costs energy and you only have a finite amount of energy on your system. So eventually, but sometimes you do have to change your orbit in order to avoid running into another satellite. And here, what we showed is that there is this trajectory with a finite memory policy. So you have 5 internal memory states, and you can find that one. And so this yields a significant reduction in trajectory length and cost over the solutions that other approaches found. And what we're actually doing in order to solve this is we're solving a Markov chain with 200,000 states and up to 10,000 parameters in order to do this. And we're using this SCP technique in order to get to such a solution in a couple of minutes. Yeah, so I'm not going to go into the details here. I'm also going to skip the work on Bayesian networks. The only thing I really want to highlight here is that if you have Bayesian networks, Joost-Pieter said you can translate them into a Markov chain in order to answer standard evidence queries. You can do the same thing if your Bayesian network is actually parametric. So the typical Bayesian networks, you have these conditional probability tables. And here we're now allowing conditional probability tables that have symbolic probabilities in there. If you're interested, I warmly recommend looking into this paper. I now want to go briefly into product lines. So a product line is another type of parametric system. So you can think about a car in a very abstract way as being defined by a set of wheels and the engine that your car is running. And for show effect, I'm taking a steam engine here. Now what you're actually analyzing are 8 different cars. If we pick, for example, this, what I would call the ancient car configuration, then we know how to create a Markov chain to evaluate the reliability, right? That Markov chain might be coming from a fault tree, that might also be coming from a prism file, but we know how to do these things. Now, the important thing is that if you're changing your product, you're not changing your complete Markov chain. Typically, there are these variation points. And for example, if we're changing the engine, then in these states, the reliability is affected by the choice of engine. So your Markov chain will change in these states. But the rest of the Markov chains remains untouched. If you change your wheel, then maybe we're going into a different state there. But the rest of the Markov chain remains untouched. And this kind of idea is really essential if you want to analyze large sets of similar Markov chains at the same time. And you can really think about this as a parametric Markov chain again, just with the difference that we're no longer changing the probabilities, but we're now changing the destination of those transitions. So in a simplified and informal way, what you can think about here is that we have a bunch of states, 0 to 11, and now we have parameters that exactly say this, to which state are we going? And now, for example, if we're thinking about defining this Markov chain, then we can say, well, there's a transition from state 0, and with probability 1, that goes to some state h. From state 1, we'll just have a regular distribution to some successor states and so forth. And then from state 7, we might say, with some probability, we go back to state 4. And with probability 0.8, we go to state k, whatever the value of k might be. Now, this maybe looks a little bit strange to you. Why would you actually model it like this? Let me first, just to clarify, right? So if we now pick constant concrete values for h and k, we will just get a concrete Markov chain. Now, why would you model it like this? Well, here is a prism file that exactly is doing what I'm telling you on the left. I define 2 constant integers, h and k, And now I'm just saying, well, the new value of S will be this constant integer H, and the new value of S in these states will be this new value K. And now suddenly it all becomes very natural. So you give a prism file and you're asking, what values should I pick for H and K in order to find, to make sure that the probability to reach a red state is bigger than some lambda. As Joost-Pieter said, we have a tool called Paint, which does this. It's open source available on GitHub. And here, as an example, there's the disk power manager. So what you can think about is we have a service requester. It generates requests, and we put these in a queue. Then from this queue, we can take requests, put them into the service provider. The service provider can constantly decide whether it should be sleeping, idle, or active in order to save power, and on the other hand, make sure that we quickly enough ensure that we're handling these requests. The question that we have when we're building such a system is maybe, depending on the queue, what power profile should we pick? And so here we said, let's define a couple of regions between T1, 0 and T1. Some power profile should be used. We call that power profile P1. Between T1 and T2, we are going to use maybe a different power profile. We call that P2, and so forth. Right, and now how do we choose these values? In particular, also, how do we choose the queue size? Depending on a specification that maybe says the expected number of lost requests must be at most 1, and the expected power consumption must be minimal. Now we can put this into Paint, right? So here we provide a prism file where you see now these constant integers appearing in several places. There's a large README which goes through this file in detail. And then what Paint does is it gives you some output, right? That says maybe there were 8 variables that we needed to synthesize. That means that there are 29,000 Markov chains that we would have to analyze. I'm not going to explain all the other outputs. Maybe here the average DTMCs here are very small, like just a couple of hundred states. But then it tells you, well, after some iterations, this is the optimal whole assignment. In particular, the number of iterations is still quite close to the family size, but we did not evaluate every Markov chain independently. Now, we can also look at a variation of this, which is more realistic. So now we have different priority queues for high priority and low priority requests. If we do this, we get 20 parameters. We now get into 1 million different Markov chains, and all these Markov chains now have a couple of thousand states. We still have the same specification as before. And so indeed, there are 43 million programs that we're considering. And within 9 hours, we find this optimal instantiation of this of these parameters. The baseline methods that would go over all these things would take, even with Storm, more than a month to compute this value. Okay. This is the end of the parametric part. I wanted to thank our co-authors on the parametric things, because all of this work is based on lots of corporations. And I wanted to highlight that there are 2 papers that I find particularly relevant in order to, if you want to get into this topic more. And they will also have all the references that I had on the slides. And of course, you can always get in touch with us if you prefer that over paper reading. In a discussion with Farid before the tutorial, we were also a little bit discussing, like, okay, this is a very symbolic version of AI. Can you say a little bit on how this relates to deep reinforcement learning? And I am going to show you one aspect here, and that's the notion Maybe I'm going to skip this part. Sorry for that. At least if I'm able to, yes, in the interest of time. And that is called runtime monitoring. So here, the challenge is as follows. You have an advanced controller, maybe for driving your vehicle, for deciding whether or not you can land as a plane. And there's a safe controller, and that does something that is deemed safe in all kinds of situations. Now the question is, which of these two controllers should you trust? Maybe you always trust your safe controller, but your safe controller will not have the performance that your advanced controller has, right? If your car says, well, the safe thing to do is just find the nearest parking spot and never exit there, then that's not a good decision to always use the safe controller. And so you have two controllers, they both put an action, and that action is going to update your environment, and that leads to sensors that, again, feed into your controllers, but also in your decision module. And so in particular, you don't know really in which state your system is, but you only have a view on the environment through your sensors and your perception modules. And this is one question that Boeing in particular asked us, where this is a simplified setting, of course. There's an aircraft that's still 10K away initially. It approaches an airfield. There are some ground vehicles 04 and 05 that move around based on some stochastic model. And we have to decide, should we continue landing or should we initiate a go around and say, well, it's too risky. And those vehicles might be on the, might actually enter the airstrip. Okay, so that's a question to ask. I'm not going to reveal what's happening. So our approach here is most easily explained from the right. So we're creating this decision module. It outputs a verdict. In this case, it's outputting OK. And it's doing that based on the probability that our vehicle and our plane would collide. And that's done with a reachability analysis. And that's where Storm is coming in. So in order to obtain this worst case probability of actually colliding with the aircraft, we're taking Storm, where we do some filtering based on what the vehicle is doing, and we get some information from the plane. We run Storm, and that provides us with this probability. And in this example, we're doing exactly this with two vehicles. So what you can see here is that this plane is arriving. The vehicles are arriving with roughly 9 meters per second. They're going towards. We still have some time. We still have 40 seconds. So there's no need to say, okay, right. So the probability of was still around a half, but that's fine. But now at this point in time, we can see that this vehicle has slowed down significantly. And based on the model that we have and the information that we have, we can say, well, within 17 seconds, this vehicle is not gonna enter the airstrip. So here the probability is actually not zero, but very close to zero. And on the other hand, this vehicle has not slowed down. And so the worst case probability based on the model on this MDP that we were provided with, it says, well, you should assume that this vehicle is actually gonna enter the landing strip. And so this will lead to what is called a close encounter. It will not lead to a crash, but to a close encounter. And in order to avoid this close encounter, the decision module would say, please abort the landing here. So this is one part where Storm is inside of an application where the airplane is further an autonomous drone. So that's the end of the theory part. I will show you a little bit more on the hands-on session now. So, but if there are any questions, maybe let's do them now first. Okay. Okay. Yes, Maximilian.
Yeah, just a quick one. Like, was this airplane scenario a discrete state or a continuous state or discrete action, continuous action scenario?
That's a great question. So the model that we were provided with is a continuous model. So there was basically a rule book which said like this is how ground vehicles behave. We discretized this in a way that it's actually over approximating the worst case probabilities. So that's also, so the actual model was actually fully stochastic. And by abstracting this into a finite discrete system, we obtained a discrete state, discrete action MDP, with the guarantee that the probabilities that we're providing are over approximations of the actual probability.
I see, right. But overall, it's like a limitation of the, like continuous states or continuous actions are just not possible right now, I guess.
No, they're not possible. No, that's especially not with the techniques we've been talking about today, because we're explicitly storing transition systems. But we see that many people working on continuous models here in Nijmegen or in Oxford, they are actually using Storm under the hood. They're doing this abstraction in order to obtain their policies. Definitely a limitation. So in the interest of time, let me say a few final words on the model checking part. Today we've been talking about things where we are explicitly representing transitions. That's not necessary, and actually lots of research, in particular from Joost-Pieter's group, is going on where we use the structure of the PRISM program or any other high-level representation and work directly on that. And that makes it possible to go into situations where you have more than billions of states. There's a lot of work going on verification of partially observable MDPs, not just via the parameter synthesis, but in lots of other directions. We've not talked about those today. There's lots of work on multiplayer MDPs and stochastic games, also not covered, but lots of interest also on our side. We looked at parametric Markov chains. You can also look at parametric MDPs and ask questions like, is there a policy such that no matter what the probabilities do? That's an active area of research. And I showed you in StormPy how to extract policies, but they were still tabular representations. And of course, we are aware of all the function approximations. We are also aware of all the work on learning decision trees that represent these policies. And so that's definitely also an interesting area of research. And in order to avoid swapping back and forth, I will say these almost final words now before going on to the hands-on session with some final thoughts. If you have any features where you feel like, oh, I would like to use Storm, but this is really missing, we would love to hear about those. And also, if you feel like you have a case study or something, we would love to hear about those because they really drive our research forward and to understand where is Storm currently lacking in support, and that's what we want to investigate, right? We have lots of our own ideas, but fresh case studies are almost the thing we would like to get out of these kinds of things the most. Your email addresses, and right now, without further ado, I would go to the hands-on thing. I wanted to show you two things before really wrapping up. So I hope you do see my slides. And let me continue where we stopped before. That's the robustness with parametric Markov chains. And I wanted to show you one example where you can really see how flexible things are and what kind of cool things you can do on top of the things we've seen. So we're still in our grid world, and we have a property that tries to minimize the movement costs, the expected movement costs to get to the station. and we can model check this, and we can obtain a scheduler. Then the result is that within 5.76 steps in your grid, you can reach your station. Now, what we want to do is we want to use the parametric part. And so now the slippiness, I told you earlier, we are in this grid world, and there's some probability that you're not actually making any progress. And so here we have this probability P, which ensures that you're updating, that you're going one step. And with probability 1 minus P, you would actually go 2 steps into a direction. The rest of this program is still the same. And then what we can do is we can say we're now creating a parametric MDP with this slippiness. So we're taking this program, but now we're defining the constant n to be 6. And we say, well, Q and P should be the same. Why? Because that makes everything one-dimensional, and that is a little bit easier to plot. So we still have a model, and now what we can do is we can say we have this scheduler that we computed beforehand for the concrete model with a fixed slippiness, and that was optimal under those conditions. Now we can ask, well, how is the number of steps in order to reach the station depending on this parameter P, which induces the slippiness? And then you'll get this function, which, like before, is hard to grasp, but we are in Python, so that's nice. We can just plot this using NumPy and matplotlib, and we see that if this slippiness approximates 1, then we're most of the time actually doing 2 steps, and that's great because for this policy you will actually reach the target. You're moving very fast. On the other hand, if your slippiness is very low, then you most of the time just do 1 step, so you need more steps to reach the target. But on the other hand, you have this more fine granular control of where you're going, so that's also beneficial. And the worst case is actually somewhere in the middle. So this gives you some insight into the sensitivity of your policy depending on the slippiness in the grid. Now you can even go 1 step further and say, okay, so say that we first now going to compute another policy, and that policy is going to try to optimize the best case slippiness for any slippiness value between 0.1 and 0.2. And we also find the associated expected movement cost. Now, what it turns out is if your slippiness is between these values, then you can actually do this with in 8.7 steps. And the worst case is at this value for P. And now we can also compare this to what happens at this point with our previous scheduler that we had. So we know the best case scheduler here achieves this in 8.7 steps. And the scheduler that we're considering, that we analyzed earlier with model checking it at a fixed value for P and Q, that requires actually 9.7 steps here. And so that gives you an insight on how, not just how sensitive are we in order to compare to the parameter value, but also how bad is the scheduler that we have compared to a version that would optimize this in on this range between P equals 0.1 and 0.2. So this is as a highlight where these things you cannot do on the command line, right? And this is actually a piece of code that is nowhere in Storm doing this story. This is really something that you can do because there's this Python API, which is very rich and which allows you to go down into details. It's the final words. Maybe one thing which is often interesting for people that want to connect this to reinforcement learning is that we have simulators which are very similar to the PyGym environments that are standard in all the reinforcement learning things. And you can either do that on the level of the program, so there you have features X and Y, or you can do this on the level of the model, and then so there are different ways of doing the simulation based on whether you actually start with a Prism program or with a model, an explicit state model. Then Joost-Pieter also showed DFTs, and the notebook, there's a different notebook in your JHub that shows you what to do with dynamic fault trees. I just want to highlight that this notebook contains all the information that Joost-Pieter talked about before. So for example, you can use a simulator to really try to understand the semantics of a fault tree. So you have some initial state here for your simulator where everything is operational. And then you can say, let us fail some element P1. Then P1 is fails here. And then you can continue your simulation and say, maybe now also the component SW is going to fail. This means that a whole lot of other options become don't care, and the overall system failure is now triggered because here's an OR gate, there's an OR gate. So a failure of software immediately leads to an overall system failure. So if you want to understand fault trees, there's a lot of things that you can do via these Python bindings. You can also do the model checking. And as a very last item on this notebook, there is a way to understand the partial state space building. So what you can see in this graph, what we actually plotted, are the different iterations of building and verifying the Markov chain. So in the first iteration, or in the first second, what has happened? In the first iteration, what we do is we build the first 18 states on the right, and that leads to a lower bound and an upper bound between 0.4 and 0.55% of system failure. Now we can continue our system building, and then we obtain already quite tight results. And then if we continue, we eventually build the full state space here of 25 states, which also yields a perfect state. Why am I showing you this? If for some of these models, for these DFTs, there's a lot of domain-specific knowledge, and our API is typically flexible enough that you can actually steer some of this partial state space building based on the information that you have. So again, there's the off-the-shelf usage of Storm, which is great to start with. But if you feel like the system is not scaling to your case study right now, there's actually a lot that the API already allows you to do, or things where we can help you to get the most out of Storm with this API. And with that, I would like to conclude. I had a lot of fun presenting this. I hope that the combination of theory and practice, like hands-on session, really makes it easier to start with Storm and StormPy. We do realize that we're providing academic software, so please let us know if you have any problems with it. We're more than happy to accommodate any questions and try to help you get started with Storm. On the other hand, we already have a couple of hundred happy users, so even if this looks daunting at first, it's always nice for us that we see people pushing out case studies with Storm that never ever contacted us on the go, and then we are suddenly surprised by case studies on soccer simulations or cryptocurrencies that are using Storm.